Hello there and welcome to Physics with William, where curiosity slows down a little and science is allowed to breathe. Tonight we're stepping into a part of physics that sounds almost made up at first, like something a theorist would whisper into their coffee and then immediately regret saying out loud in front of the experimentalists. And yet here we are, with some very serious people in very serious buildings, asking whether most of the universe may be hiding in plain sight, just beyond the reach of everything we have confidently called known physics. Before we get into all of that, I would love to know where you're listening from tonight. What time is it in your corner of the world right now? There is something fitting about that question, because this story is really about perspective, about how much of reality may be sitting all around us, while we notice only the small familiar part that talks to our instruments in the usual ways. So while one part of the world is getting ready for bed and another is starting the day, we are all meeting here to consider the possibility that the universe has been keeping a very large secret. And if you enjoy this slower kind of physics, if this is the sort of thing that helps you unwind while your brain remains just curious enough to stay pleasantly occupied, do leave a like and subscribe. It helps this small, calm corner of science find more people who enjoy big questions explained without anyone shouting at them, which, let us be honest, is not always guaranteed online. Now then, the question at the centre of tonight is simple to ask and much harder to answer. Did CERN just find the dark sector? And if the answer turns out to be yes, even in part, then the implications are not small, not tidy, and not especially convenient for the standard model of particle physics, which has spent the better part of the last century becoming the most successful scientific framework ever built. It has predicted particles before they were found. It has described forces with astonishing precision. It has survived test after test after test, with the calm expression of a student who somehow always leaves the exam room early and still gets full marks. And yet, for all its success, it also has an awkward blind spot the size of the cosmos. Because when we look out at the universe, really look, using galaxies, galaxy clusters, the afterglow of the early cosmos, and the way matter gathers under gravity, we keep running into the same uncomfortable fact. The ordinary matter we know and love, the matter in stars and planets and people and biscuits and old notebooks and laboratory walls, appears to make up only a small fraction of what is actually out there. Most of the matter in the universe does not shine, does not absorb light in the usual way, and does not fit neatly into the collection of particles that the standard model offers us so proudly. That alone would be enough to keep physicists awake, but the deeper worry is even stranger. It is not just that something is missing from our inventory. It is that whatever is missing may not be a single extra particle that we forgot to include at the back of the textbook. It may be an entire hidden world, a sector, a shadow set of particles with its own interactions, its own structure, perhaps even its own complexity, brushing against our world only faintly, like a conversation happening behind a wall. This is where the phrase dark sector comes in. It does not simply mean dark matter in the sense of one unknown invisible substance. It points to a broader possibility, that beyond the particles we know, there may be additional particles, and perhaps new forces as well. Not fantasy forces, not magic, just interactions that are real, but very weakly connected to ordinary matter. Weakly enough that we have not seen them clearly yet. Strongly enough, perhaps, to leave odd hints in the right experiments if we look with enough patience and enough skepticism. And this is why people pay close attention when CERN data does something mildly impolite. Most of the time, particle physics is not built on dramatic discoveries appearing in a single afternoon. It is built on statistics, on tiny excesses, on patterns that may disappear next year or sharpen into something impossible to ignore. So when headlines say physicists are panicking, it is worth translating that into more realistic laboratory language. They are not running through corridors dropping clipboards. This is not that kind of panic. It is the quieter, more professional kind. The sort where researchers stare at a plot longer than usual, rerun the analysis, call a colleague, recheck the detector calibration, and begin speaking in sentences that start with, I do not want to overinterpret this, but that kind of panic is far more interesting. To understand why, we should begin with what the Standard Model actually is. In broad terms, it is our best description of the basic particles and the forces that govern them, apart from gravity, which remains the difficult relative at the family gathering. The Standard Model includes quarks, which make up protons and neutrons. It includes leptons, such as the electron and its more massive cousins. It includes force-carrying particles, the messengers of electromagnetism, and the nuclear forces. And after a long search, it also included the Higgs boson, whose discovery at CERN in 2012 filled in one of the biggest missing pieces and felt for a moment like the triumphant completion of a very difficult puzzle. Except it was not the completion at all. It was more like finishing the visible part of the puzzle and then realizing the table beneath it extends 3 meters farther in every direction. Because the Standard Model does not explain dark matter. It does not explain why neutrinos have mass in the way we observe. It does not explain the overwhelming dominance of matter over antimatter in the universe. It does not include gravity in a quantum framework. It does not tell us what dark energy is. It is extraordinary, but incomplete. And physicists know this. They have known it for years. The discomfort lies not in realizing there are gaps. The discomfort lies in how stubbornly nature has refused to tell us what belongs in them. For a while, many hoped that the next layer of physics would be comparatively tidy. Perhaps supersymmetry would appear, extending the Standard Model with a partner for every known particle. Perhaps weakly interacting massive particles would show up in detectors or collisions and elegantly account for dark matter. Perhaps a new symmetry would reveal itself and pull several problems together with the satisfying click of a well-made lock. But nature, as ever, has shown no obligation to make things tidy for us. Instead, one possibility that has steadily gained attention is less like adding a missing tile, and more like discovering that the house has a hidden annex. Imagine that the particles of the Standard Model are not the whole cast, just the loud, well-lit characters on the front of the stage. Now imagine there are others in the wings, mostly interacting among themselves, rarely stepping into the light. They may have their own force carriers, their own equivalents of familiar interactions, perhaps even whole chains of decay that mostly remain invisible to us. If those hidden particles couple only very weakly to ordinary matter, then our detectors would not register them directly in the usual way. What we would see instead are indirect clues, energy appearing to go missing, strange decay patterns, unexpected excesses, a particle that seems to live longer than it should, a resonance where no resonance ought to be, a decay channel that opens like a trapdoor into something unseen. This is the logic behind many modern searches at CERN. Particle colliders are sometimes described as machines for smashing particles together, which is true, but slightly undersells their elegance. They are also machines for manufacturing unfamiliar conditions. When protons collide at enormous energies, they do more than break apart. They can create massive unstable particles that do not normally exist in ordinary environments. If there are hidden sector particles that can be produced in those collisions, then the Large Hadron Collider becomes one of our best chances to catch them in the act. Not by seeing a little sign that says hidden particle here, unfortunately. Nature is rarely so considerate. We have to infer. We examine what flies out of the collision point. We reconstruct the tracks. We calculate momentum and energy balance. We look for displaced vertices, where a particle appears to travel a measurable distance before decaying, a sign that something unusual and slightly reluctant to interact may have been produced. We search for events with missing transverse energy, where part of the collision outcome seems to have slipped away into particles that do not talk to the detector very much. We look for narrow bumps in distributions that might indicate a new mediator. We compare again and again against the predictions of the Standard Model, which remains annoyingly good at explaining most things until it does not. One especially intriguing idea in this landscape is the dark photon. The name sounds glamorous, perhaps slightly comic book, but the concept is fairly sensible. We know the ordinary photon carries the electromagnetic force. A dark photon would be a similar force carrier associated with a hidden sector, potentially mixing very weakly with the ordinary photon. That tiny mixing could provide a portal, a narrow bridge between our visible sector and the dark one. Not a wide open gate, more like a creaky side door. Enough for rare effects to show up in experiments if we are lucky and careful. If such a particle exists, it could help explain how dark matter interacts. Not strongly enough to have been obvious long ago, but enough to leave faint signatures. It could change decay rates. It could create new channels in collider events. It could even reshape the way we think about cosmic history, because the early universe would then have contained more than the particles we usually include in the story. It would have had extra ingredients, extra interactions, extra thermal histories unfolding in parallel with the one that led eventually to atoms, stars, and the mildly chaotic business of human civilization. And that is where the stakes become very large, very quickly. If the dark sector is real, then our universe may be less like a single coherent inventory, and more like a layered ecosystem. The visible matter we're made of would be only one branch of a much bigger structure. The ordinary forces would not be the whole list. The early universe would need to be rewritten in important places. Models of structure formation, dark matter production, cosmic evolution, perhaps even inflation and reheating, could all be affected depending on how rich and how active the hidden sector turns out to be. This is why a genuine hint from CERN would not feel like just another incremental result. It would be the opening of a door that many suspected was there, but nobody had yet pushed wide enough to see through. And once that happens, the standard model stops looking like the nearly complete rulebook of matter and starts looking more like a beautifully detailed local map of one neighbourhood. Still, caution matters here. Physics is full of anomalies that fade with better data. A bump appears, excitement grows, seminars multiply, and then 6 months later, the result dissolves into statistical dust. Particle physicists are used to this cycle. They have the emotional posture of people who have been ghosted by significance more than once. So the right attitude is not immediate triumph, it is sustained attention. Are multiple experiments seeing compatible hints? Do the signals survive different analysis methods? Can backgrounds really be ruled out? Is there a consistent model that explains the data without quietly breaking 5 other things we already know to be true? That last part is especially important, because new physics has to do more than be exciting. It has to fit, or at least fit better than the thing it is trying to replace. A hidden sector model cannot simply wave at dark matter and leave the rest untidy. It must respect collider bounds, astrophysical observations, cosmological constraints, and the deeply inconvenient fact that the universe keeps giving us many clues at once. Even so, the reason this idea has such staying power is that it solves a psychological problem in physics as much as a technical one. For decades, researchers have had strong evidence that something important is missing. Dark matter is not a decorative mystery. Galaxies rotate in ways ordinary matter alone cannot explain. Clusters of galaxies bend light too strongly. The cosmic microwave background points to a universe with much more matter than we can see. So the absence is real. What nobody knows is whether that absence comes from one missing particle or an entire hidden architecture. And that is why the dark sector is such a compelling possibility. It is broad enough to be plausible and specific enough to be testable. It does not merely say there is more. It says there may be a connected realm of more. By now you can probably feel the tension that makes this topic so irresistible. On one side sits the standard model, disciplined and proven, the reigning champion of microscopic physics. On the other sits the evidence that most matter is still unaccounted for, accompanied by increasingly inventive searches for portals, mediators, and hidden particles. CERN lives right at that intersection. It is the place where theoretical suspicion meets engineered violence in the most scientific way possible. If there is a weak bridge between our matter and a darker sector, then high-energy collisions may be exactly where it flickers into view for a brief and precious moment. And if that moment is real, then the universe is not just stranger than we thought, It is stranger in a very specific direction. More populated, more structured, more layered, less complete in all the places where we once felt most confident. Which is not bad news, really. It is the kind of problem physics secretly hopes for. A problem that does not merely require polishing the decimals, but forces us to redraw the picture. So before we go further into dark matter itself, into the evidence that something unseen is shaping galaxies and the cosmos at large, it helps to sit with that discomfort for a second. We may have built a magnificent theory of ordinary matter while living inside a universe where ordinary matter is the minority presence. And to understand how we ended up in that curious position, we need to begin with the missing mass of the cosmos and the long trail of evidence that made it impossible to ignore. If you want to understand why physicists take the dark sector seriously at all, the first thing to notice is that nobody went looking for it because they were bored and wanted to make the universe sound more dramatic. That would be a very unfair summary of modern cosmology, although not a completely impossible one on some very long Thursdays. The real reason is much simpler. When astronomers began measuring the universe carefully, the numbers kept refusing to behave. For a long time, the basic assumptions seemed perfectly reasonable. You look out into space, you see stars, gas, dust, planets, glowing nebulae, bright galaxies, and the hot material between them. You add it all up, and you expect that what you can see is more or less what is there. Perhaps not every grain of matter is glowing at any given moment, but surely most of the mass in the universe should in some way belong to the ordinary family of things that emit light, reflect light, absorb light, or otherwise announce their presence. That was not a foolish assumption. In everyday life it works very well. If you walk into a kitchen and want to know where most of the matter is, the answer is usually not hidden in some invisible parallel pantry. It is the table, the chairs, the bread, the mug, the person searching for the mug, and the cat who has chosen the exact wrong place to sit. The cosmos, unfortunately, is not a kitchen, and it turned out to be much less cooperative. One of the earliest serious clues came from galaxy clusters. These are enormous collections of galaxies bound together by gravity, not casual arrangements, but vast systems moving under their mutual pull. In the early 20th century, astronomers began studying how fast galaxies inside these clusters were moving. The logic was straightforward. If you know how quickly the galaxies are orbiting within a cluster, you can estimate how much total mass must be present to keep the system gravitationally bound. Too little mass, and the galaxies should simply fly apart. Enough mass, and the cluster holds together. What researchers found was deeply awkward. The visible matter did not seem to provide enough gravity, not even close enough to fix with a bit of observational uncertainty and a patient tone of voice. The galaxies were moving as though the cluster contained far more mass than anyone could see. This unseen mass became known as missing mass, which is not the most glamorous phrase in science, but it has the virtue of honesty. Something appeared to be there gravitationally, yet not there optically. The universe had begun failing a very basic accounting test. At first, you might be tempted to say that astronomy is difficult and distant things are messy. That is a fair instinct. Many strange results vanish when measurements improve. Perhaps the light had been underestimated. Perhaps there was more ordinary gas than expected. Perhaps some assumption about the cluster dynamics was wrong. Physicists and astronomers are not usually eager to overthrow established pictures when a more modest explanation might do. The trouble was that the problem did not go away. It resurfaced again and again in different forms at different scales using different methods. The most famous version of the same issue appeared in the study of individual galaxies, especially spiral galaxies. A spiral galaxy looks, at first glance, like a fairly intuitive object. Bright stars gather toward the centre, with the luminous disk spreading outward in graceful arms. If most of the mass is concentrated in the bright central regions, then stars farther from the centre should orbit more slowly. This is the same broad logic that makes the outer planets in our own solar system, move more slowly around the Sun than the inner ones. The farther away you are from the main concentration of mass, the weaker the gravitational pull should become in the relevant sense, and the orbital speed should drop. But when astronomers measured how fast stars and gas clouds were actually moving in the outer parts of spiral galaxies, the decline they expected simply was not there. Instead of falling off neatly, the rotation curve stayed surprisingly flat. Stars far from the centre were moving much faster than the visible matter alone could account for. It was as though every galaxy was embedded in a huge extra halo of mass, extending well beyond the region where most of the light was coming from. This was not a tiny discrepancy. It was not one annoying outlier. It was a pattern. Galaxy after galaxy behaved as if surrounded by an invisible structure. The luminous material looked like only the central garnish on a much larger gravitational meal. At that point, the problem became harder to dismiss. If clusters of galaxies needed more mass than they appeared to contain, and individual galaxies also needed more mass than they appeared to contain, then perhaps the issue was not a local observational mistake. Perhaps the universe genuinely contains a large amount of matter that does not shine. That idea, once introduced, sounds deceptively simple. You might think the next step would be to ask what kind of ordinary dark stuff could do the job. Could there be many faint stars too dim to see? Could there be cold gas clouds? Could there be black holes scattered everywhere in sufficient numbers? Could the missing mass just be normal matter hiding badly? People considered all of those possibilities. That is exactly what science should do. Before inventing a new category of matter, you first ask whether the old category can be stretched a bit farther. But over time, those ordinary explanations began to fail. Too many dim stars would still have consequences for how galaxies formed and how much light should emerge overall. Vast clouds of ordinary gas would leave signatures. Huge populations of compact objects could in some cases be constrained by their gravitational effects on passing light or by other observational methods. One by one, the familiar hiding places became less convincing. Meanwhile, the evidence grew richer. Gravity, helpfully and somewhat ominously, does not care whether matter is luminous. It responds to mass itself. That means the universe gives us a second way to detect unseen matter, by watching how it bends light from background objects. This effect, known as gravitational lensing, follows from the idea that mass curves space-time and therefore alters the paths that light takes. When a massive object lies between us and something more distant, it can distort the image of that background source. In some cases, the effect is subtle, a slight stretching or skewing. In other cases, it can be dramatic, producing arcs or even multiple images. This turned out to be a powerful tool because it allowed astronomers to map where mass is, not by where it shines, but by where it bends. And once again, the answer was uncomfortable. The lensing signal often indicated much more mass than visible matter could explain. Even more interestingly, the inferred mass distribution often extended beyond the stars and gas in exactly the sort of way expected if galaxies and clusters sit inside larger halos of unseen material. So now the missing cosmos was being described in several independent languages. The motions of galaxies and clusters were telling one story. The rotation of stars and galaxies was telling another. Gravitational lensing was telling a third. They all pointed in the same direction. There is more mass in the universe than meets the eye. It is worth pausing here because this is one of those moments in science where the accumulation matters more than any single result. One odd measurement can be wrong, two can be suspicious, but when many different methods with different assumptions converge on the same basic conclusion, the case becomes much harder to ignore. By the time the evidence matured, the question was no longer whether something was wrong with the simple, visible matter picture. The real question had become what exactly was missing. Then cosmology entered the conversation and made everything bigger. When we study the universe on the larger scales, we are not just looking at isolated galaxies. We are looking at the whole cosmic web, the vast pattern of structure stretching across space. Galaxies cluster into groups and clusters and long filaments, with great voids in between. This large-scale structure did not appear instantly. It grew over time from tiny fluctuations in the early universe. So if we want to know what the universe is made of, we can ask not only what gravity is doing now, but how structure managed to form in the first place. That brings us to one of the most important sources of cosmological evidence, the faint afterglow of the early universe known as the cosmic microwave background. This radiation comes from a time when the universe was much younger, long before stars and galaxies as we know them had fully formed. It carries a record of tiny density variations in the early cosmos, the seeds from which later structure would grow. What makes this so powerful is that the pattern in that ancient light depends sensitively on the ingredients of the universe. The amount of ordinary matter matters, the amount of non-ordinary matter matters, the expansion history matters, the overall geometry matters. It is like being handed a snapshot of the universe as an infant and realizing that the details of the face already tell you a great deal about the adult. When physicists analyze this ancient radiation with increasing precision, the result again pointed to the same broad picture. Ordinary matter is only a minority component of the total matter budget. There is additional matter that exerts gravity, but does not behave like the familiar baryonic matter that makes up atoms. In other words, the missing cosmos was not merely an issue inside certain galaxies or clusters. It was woven into the global composition of the universe itself. By this stage, the case for dark matter in some form had become extraordinarily strong. Not because one experiment said so, but because the universe kept repeating itself. It repeated itself in galactic rotation. It repeated itself in cluster dynamics. It repeated itself in lensing. It repeated itself in the microwave background. It repeated itself in the growth of large-scale structure. The missing mass was no longer a fringe idea. It was part of the standard cosmological picture. And yet, there was a catch. Because of course there was. Knowing that unseen matter exists, or at least that something behaves exactly as if unseen matter exists, is not the same as knowing what that matter is. This is where public descriptions of dark matter can become accidentally misleading. Sometimes it is presented as though astronomers discovered a hidden substance, and now we are merely polishing its label. That would be lovely. In reality, what we discovered first was a gravitational problem. The invisible matter interpretation is currently the leading framework because it explains many observations very well. But the exact identity of the responsible ingredient remains unknown. This distinction matters because it opens two very different lines of thought. One possibility is that there really is a new kind of matter, made of particles outside the standard model. These particles would be massive enough to gravitate, stable enough to survive since the early universe, and dark in the sense that they interact weakly or not at all with light. This is the route that leads naturally toward hidden sectors, dark photons, and all the other fascinating suspects that now populate theoretical physics. The other possibility, at least historically, was that perhaps gravity itself behaves differently on large scales than we thought. Perhaps the apparent missing mass is not matter at all, but a sign that our laws of motion or gravity need modification in certain regimes. This alternative has never gone away entirely, and it is intellectually important because science works best when strong claims face strong competition. But although modified gravity ideas can explain some observations, they have struggled to account for the full range of evidence as cleanly as dark matter models do, especially when multiple independent datasets are considered together. There is one famous observation that pushed many researchers even more strongly toward the dark matter interpretation. This came from colliding galaxy clusters, where astronomers could compare the distribution of ordinary hot gas with the distribution of total mass inferred from gravitational lensing. In such collisions, the hot gas, which makes up much of the visible ordinary matter in clusters, can slow down and interact. But if a large amount of mass is carried by some non-luminous, weakly interacting component, then that component can pass through the collision more easily. What observers found was that the mass inferred from lensing did not stay neatly aligned with the visible gas. Instead, much of the gravitational mass appeared offset as though most of the mass had behaved like a largely collisionless substance rather than like ordinary matter. That kind of result is not absolutely the end of every alternative idea, but it is certainly the sort of thing that makes people sit up straighter in seminars. Because it suggests that the missing component is not just a bookkeeping device. It behaves like something real and distinct. By now, you can see why physicists began to talk less about an isolated anomaly and more about a hidden component of the cosmos. The universe was not merely lighter or heavier than expected. It seemed to contain a whole category of matter that ordinary particle physics did not explain. And this is where the emotional tone of the subject becomes very interesting. On paper, dark matter sounds like a technical gap. In practice, it is a profound insult to our confidence. We built a detailed theory of ordinary particles. We learned how atoms work, how stars shine, how nuclei behave, how light and charge and quantum fields fit together with remarkable precision. Then the universe looked back at us and quietly indicated that all of that wonderful knowledge describes only a small fraction of the actual matter content of the cosmos. It is a bit like spending decades mastering the layout of a city, and then discovering that most of the population lives underground and has somehow neglected to tell you. So when people say that most of the universe is dark, they do not mean spooky in the childish sense. They mean inaccessible through ordinary electromagnetic observation. They mean silent to telescopes in the usual ways. They mean present through gravity and perhaps through other faint effects, but not obviously part of the luminous world we first learned to measure. Dark is not a poetic label here. It is a statement about interaction. That point becomes crucial later, because once you accept that the missing cosmos may be built from particles outside the standard model, you have to ask how hidden those particles really are. Do they interact only through gravity? Do they have their own forces? Can they occasionally communicate with ordinary matter through a weak portal? Are they one simple particle species or an entire population? In other words, is dark matter just one missing entry in the inventory, or is it evidence that our visible world is only one sector among several? That is the larger possibility that now makes the subject so electrifying. A hidden sector is not merely a fix for galactic rotation curves. It is the suggestion that the unseen matter of the cosmos may come with its own internal physics, its own structure, its own carriers of force, perhaps even its own complicated history in the early universe. That is a much bigger claim than saying there is extra mass. It is saying that the universe may be organized in layers, and we happen to occupy the bright, noisy one. Even before we get to those more ambitious ideas, the central fact remains beautifully stubborn. The cosmos does not balance if you count only what shines. Every time we weigh the universe by gravity, it comes out heavier than the visible parts allow, and not by a little. By enough to force a serious revision of our picture of reality. This is why the missing cosmos matters so much for particle physics. Cosmology did not merely hand particle physicists a curious astronomical puzzle. It handed them evidence that the known particle catalogue is probably incomplete. If most matter is not made of particles in the standard model, then the standard model, for all its brilliance, is not the whole story of matter in the universe. It may be a local success within a much larger framework. That realization changed the mood of fundamental physics. It meant that the search for new particles was no longer just a matter of elegance or theoretical ambition. It became a necessity imposed by the sky itself. Galaxies were effectively telling collider physicists that they had homework, and that is where our path naturally leads next, because once the universe has informed you that most of its matter lies outside your best existing theory, the obvious question is how much of that theory still feels complete, and where exactly the cracks begin to show when you examine it closely enough. The difficult thing about criticizing the standard model is that it keeps deserving respect. It is not one of those theories that survives because people are too attached to it to let go. It survives because it works, over and over again, with a level of accuracy that would be almost irritating if it were not so impressive. When physicists compare its predictions with experiment, the agreement is often so good that the remaining discrepancies begin to look less like failures and more like the universe teasing us on purpose. So when people say the standard model is incomplete, that statement needs to be handled with care. Incomplete does not mean weak. It does not mean broken in any simple sense. It means we have an extraordinarily successful description of ordinary matter and ordinary forces, and at the same time we have very strong reasons to believe that this description does not cover the full content of reality. That tension is exactly what makes the subject so compelling. If the theory were obviously bad, replacing it would be easy in principle, even if difficult in practice. If the theory were truly final, there would be nothing left to hunt for in this direction. But the standard model sits in the more interesting and more uncomfortable middle ground. It is good enough to command confidence, and limited enough to make that confidence uneasy. To see why, it helps to remember what the standard model actually does. At its core, it is a framework for describing the basic particles that make up visible matter and the interactions that govern them. It tells us about quarks, which combine to form protons and neutrons. It tells us about leptons, including the electron and the neutrinos. It includes the carriers of the electromagnetic force and the strong and weak nuclear forces. It also includes the Higgs field and its associated particle, which help explain why certain particles have the masses they do. When you lay this out in a textbook or on a neat classroom chart, it can look almost tidy, even elegant, as though the universe had the good manners to organize itself into categories for our convenience. What is remarkable is that this is not just a convenient story, it is a predictive machine. The standard model does not simply label particles after they are found. It gives precise relationships among processes, decay rates, scattering outcomes, and interaction strengths. It has guided experiments for decades. It predicted particles before they were observed. It survived the discovery of the W and Z bosons. It absorbed the top quark. It waited for the Higgs with an almost unreasonable amount of patience, and then welcomed it exactly where it had long said it should be found. There are not many theories in science that can face such a long series of tests, and emerge with their dignity so fully intact. This is why people inside physics often speak of the standard model with a kind of stern affection. They know its limitations, but they also know that dismissing it would be absurd. It is one of the greatest intellectual achievements in the history of science. It describes the behavior of known particles with extraordinary success. Entire technologies rest indirectly on the quantum field theories that support it. Much of modern physics education is shaped by the fact that this framework works so well, and yet, once you step back and ask slightly larger questions, the confidence begins to thin around the edges. The first and most obvious problem, at least in the context of our topic, is that the standard model has no viable particle candidate for the dark matter that seems to dominate the matter budget of the universe. That alone is a serious limitation. If most of the matter in the cosmos is not made of the particles included in our best theory of matter, then our best theory of matter is not the whole story. That is not a minor technical footnote. It is an enormous conceptual warning sign. It means the theory that explains atoms, chemistry, stars, and laboratory collisions still leaves out the dominant matter component in the universe at large. This does not mean the standard model becomes useless the moment dark matter enters the conversation. Quite the opposite. It remains the correct description of ordinary particles in the energy ranges and processes where it has been tested. But it does mean that the theory cannot claim finality. It is not a complete inventory of what exists. It is a very accurate map of one visible district in a much larger territory. Then there are neutrinos, which introduced a different kind of discomfort. In the original standard model picture, neutrinos were treated as massless. That seemed perfectly serviceable for a while. But experiments eventually showed that neutrinos change flavour as they travel, a phenomenon known as oscillation. And for oscillation to happen in the observed way, neutrinos must have mass. Not much mass, certainly, but not zero. That discovery did not destroy the standard model, but it did expose a missing ingredient. Some extension or modification is required to explain neutrino masses properly. Once again, the theory that looked so self-contained turned out to need help. This matters because it reveals a pattern. The standard model is not merely confronted by one awkward external puzzle called dark matter. It is already known to require some sort of addition or deeper structure in at least one other important area. So when people search for new particles or hidden sectors, they are not doing so in defiance of an otherwise complete framework. They are doing so in a landscape where incompleteness has already been demonstrated. Another major issue is the matter-antimatter asymmetry of the universe. According to our best understanding of the early cosmos, matter and antimatter should have been produced in very similar amounts. If that had remained exactly balanced, most of it would have annihilated away, leaving behind a universe full of radiation and very little ordinary matter. Yet here we are, in a universe clearly dominated by matter. Stars, planets, galaxies, and people are not a tiny correction to perfect symmetry. Something happened in the early universe that favoured matter over antimatter, at least slightly, and that slight imbalance was enough to shape everything that followed. The standard model does contain some mechanisms that distinguish matter from antimatter, but not enough to explain the observed dominance by itself, at least not in the usual understanding. So again, the theory appears insufficient at a deep cosmological level. It can describe exquisite details of particle interactions while still failing to explain one of the most basic facts about why there is any ordinary matter left to form the visible universe. And then, sitting above all of this like an uninvited but very important relative, there is gravity. The standard model does not include gravity as a quantum force. It handles electromagnetism and the nuclear interactions beautifully, but gravity lives elsewhere, in general relativity, which is itself an extraordinary theory with a completely different conceptual language. Both frameworks are immensely successful in their own domains, yet they do not merge into a single seamless description in any finished way. For everyday laboratory predictions, this is not usually a practical disaster. Particle physicists can do excellent work without quantizing gravity in most collider calculations. But at a fundamental level, the separation is another sign that our deepest theories are not yet fully unified. So by now the picture is already more fragile than the phrase standard model sometimes suggests. The name sounds complete, official, almost administrative. It sounds like a final reference manual kept in a very clean drawer. In reality, it is better understood as the current best effective theory of known particles and their non-gravitational interactions, accurate within an enormous tested domain, but almost certainly embedded within a wider framework that we do not yet possess. Still, there is a reason the cracks feel subtle rather than catastrophic. Most of the trouble appears at the boundaries. The standard model does not usually fail in the middle of an ordinary particle collision and begins smoking gently. It succeeds brilliantly where it has been properly asked to perform. The cracks show when you compare it to the universe as a whole, or when you push into phenomena that require ingredients beyond its original structure. That distinction is important because it shapes how physicists search for new physics. They are not trying to overthrow everything. They are trying to find the next layer without ruining the parts that already work. That is a much harder task than simply inventing something novel. Anyone can propose a new particle on paper. Theoretical physics is full of particles that behave beautifully inside equations and then refuse to appear in detectors, telescopes, or the early universe. The challenge is to build a model that explains what the standard model cannot explain while preserving everything it gets right. That means any serious extension must leave most successful predictions untouched, or only alter them in extremely subtle ways. It must account for dark matter without generating obvious contradictions elsewhere. It must fit collider bounds, precision measurements, astrophysical constraints and cosmological observations. Nature, in other words, has set the bar annoyingly high. This is one reason the dark sector idea has become so attractive. If new particles interact only very weakly with ordinary matter, they could remain hidden for a long time without disrupting the standard model where it already succeeds. A hidden sector does not need to bulldoze the existing framework. It can sit mostly beside it, influencing our world through faint portals, rare decays, missing energy signatures, or subtle cosmological effects. That makes it theoretically plausible in a very practical way. It offers a route to new physics that respects the stubborn success of the old one. To appreciate just how stubborn that success is, consider the culture of precision testing in particle physics. Experiments do not merely ask whether a particle exists. They ask how often a process occurs, how angular distributions line up, how decay channels compare, how symmetry patterns show themselves in measurable outcomes. The standard model has passed these tests with astonishing consistency. In some cases, theorists and experimentalists compare numbers to many decimal places and still find agreement that borders on absurd. This is not the sort of situation where you can casually insert a dramatic new force and expect nobody to notice. Any extra ingredient must be discrete, especially in the domains we've already measured well. That requirement is part of why discoveries beyond the standard model are so difficult. The theory leaves very little room for obvious mistakes. New physics, if it is nearby, seems to have chosen subtlety. It hides in rare processes, high energies, weak couplings, long lifetimes, invisible decays, and cosmological relics, rather than in loud everyday contradictions, which is, admittedly, a slightly rude way for the universe to behave after all the money we spent building detectors. There is also a philosophical side to this. The success of the standard model created a certain expectation in physics, especially during the late 20th century. Many researchers hoped that the next breakthrough would arrive in a fairly direct way. Perhaps a new symmetry would reveal itself at accessible energies. Perhaps a family of partner particles would appear. Perhaps dark matter would turn out to be one clean extension with a sensible mass range and a clear signature. There was a feeling, not entirely unreasonable, that we were close to the next obvious layer. Then the Large Hadron Collider turned on, and while it did find the Higgs, it did not immediately deliver a parade of additional particles to make the story easy. That absence changed the emotional landscape. It did not invalidate the search for new physics, but it made physicists more careful and more inventive. The cracks in the standard model remained, yet the first wave of hoped-for repairs did not simply fall into our hands. That is when the language around the standard model started to shift in a subtle way. Earlier, it was often described as incomplete, but imminently extendable. More recently, it is still incomplete, but the route beyond it feels less obvious. The missing pieces may not form one tidy upgrade package. They may instead point toward a richer and more complicated structure. Dark sectors, portal interactions, hidden valleys, long-lived particles, light mediators, and other once more speculative ideas began to attract more serious attention because nature was not rewarding the simpler expectations. In that sense, the confidence of the standard model has developed a curious dual character. On the one hand, confidence in its tested predictions remains extremely high. On the other hand, confidence that it represents the full microscopic content of reality is very low. Those two attitudes coexist without contradiction, though they can sound strange when placed side by side. The theory is both triumphant and insufficient. It is the framework we trust most in known particle physics, and one that we are certain must be transcended somewhere. This is where the phrase cracks in its confidence becomes useful, because the confidence being cracked is not the confidence of the equations in their proper domain. It is the human temptation to mistake great success for completeness. The standard model earned admiration so thoroughly that for a while it was easy to imagine the remaining work as modest cleanup. But the universe kept presenting larger demands. Dark matter was not cleanup. Neutrino mass was not cleanup. The matter-antimatter asymmetry was not cleanup. The lack of a quantum theory of gravity was not cleanup. These are structural absences, and once you frame it that way, the search at CERN looks different. It is not just a hunt for some bonus particle to make conferences more lively. It is a confrontation with the known limits of our best theory. Every search for hidden particles, every analysis of rare decays, every attempt to identify missing energy signatures or displaced vertices is part of a larger question. Where does the standard model stop being the whole story? And how exactly does the next layer announce itself? There is one more subtle reason physicists have become increasingly open to hidden sector possibilities. The standard model itself teaches a lesson about invisibility. Before certain particles were detected directly, their existence was inferred indirectly from patterns, symmetries, and missing consistency. In other words, physics often progresses not by seeing new things immediately, but by noticing that the known picture cannot close on itself without them. The current situation may be similar. We may not yet see the dark sector clearly, but the visible sector may already be hinting that it is not alone. That does not mean every anomaly is revolutionary. Far from it. The field is littered with suggestive tensions that later shrank or disappeared. Sensible physicists know this. They have learned to separate curiosity from triumph. But it does mean that the broader context has changed. A possible dark sector signal would not arrive in an intellectual vacuum. It would land in a theory landscape already marked by incompleteness. That is why even modest hints can generate such intense interest. They are not just curiosities, they are possible entry points into the region where the standard model finally gives way. So when people say the standard model is under pressure, the image should not be of a collapsing building. It is more like a structure that remains strong in the rooms we use most often, while several locked doors and unfinished corridors keep reminding us that the blueprint was never complete. We know there is more architecture beyond the walls. What we do not know is whether the next door opens onto a single extra chamber or onto an entire hidden wing. And that is the point where particle physics and cosmology start leaning toward one another very naturally. Cosmology tells us that most matter is not accounted for by the visible sector. Particle physics tells us that its best visible sector theory is incomplete in several independent ways. The idea that these two facts might be related is not merely tempting, it is almost unavoidable. If there is a hidden sector containing new particles and perhaps new forces, then the cracks in the standard model are not random flaws. They may be the edge lines of a deeper structure we have only begun to glimpse. The next question, then, is how to think about that hidden matter itself, not just as a missing entry in the cosmic ledger, but as something we can infer, test, and perhaps eventually catch through its faint but persistent effects on the world we can observe. That deeper structure becomes easier to imagine once dark matter stops sounding like a single mysterious label and starts being treated as a measured physical problem. The phrase itself can be misleading, because it makes it seem as though physicists found some black, smoky substance drifting between the stars and then gave it a dramatic name. What actually happened was more disciplined than that. Dark matter is the name we give to whatever is producing a large, repeatable set of gravitational effects that ordinary visible matter cannot explain. In that sense, dark matter is not a wild guess. It is the current best category for a very specific mismatch between what we can see and what gravity says must be there. That is why it is often described as the shadow we can measure but cannot see. The word shadow does not mean magical, it means indirect. We do not observe dark matter the way we observe a star or a cloud or a glowing disk of gas. We observe what it does to motion, what it does to structure, what it does to light passing nearby, and what it seems to have done to the universe over cosmic time. The evidence is strong precisely because it comes from many different directions at once. Dark matter has no obvious visible signature, but it leaves a gravitational fingerprint everywhere that matters. This is an unusual position for science to be in, though not an unprecedented one. There are times when a thing is discovered directly, and its properties are measured afterward. There are other times when a thing is inferred long before it is seen clearly. Neptune was predicted from disturbances in planetary motion, before it was observed through a telescope. Certain subatomic particles were anticipated from theoretical consistency before they turned up in experiments. Dark matter belongs to that second tradition, except on a larger scale and with more stubborn consequences. The universe behaves as though some non-luminous matter is present in great quantity, and it does so consistently that the burden has shifted. The real challenge is no longer to justify taking dark matter seriously. The real challenge is to identify what dark matter actually is. The reason this problem is so difficult begins with interaction. Ordinary matter announces itself in many ways because it takes part in electromagnetism. Charged particles emit and absorb light. Atoms form molecules. Hot gas glows. Dust blocks starlight. Surfaces reflect. Even when ordinary matter is cold and dim, there are usually methods for detecting it because it participates in familiar processes. Dark matter appears not to do that, or not to do it in any appreciable way. It does not seem to shine, scatter light efficiently, absorb radiation like ordinary gas, or clump into stars and planets through the same mechanisms that govern visible matter. That last point is important. If dark matter was simply ordinary matter that had gone dark, we would expect it to behave more like ordinary matter. It would cool in similar ways, it would collapse into dense structures more readily, it would reveal itself through known astrophysical processes. Instead, dark matter appears to remain spread out in large halos around galaxies and clusters. It contributes gravitationally, but it does not settle into luminous disks the way ordinary gas does. That difference tells us that dark matter is not just hidden matter in the everyday sense. It is matter with different interaction properties. One of the cleanest ways to understand this is to compare the roles of ordinary matter and dark matter in a galaxy. The visible part of a spiral galaxy, the part with bright stars and structured arms, is made of baryonic matter, meaning the familiar matter built from protons and neutrons and electrons. This matter can lose energy through electromagnetic processes. Gas collides, heats, cools, and settles. That is why galaxies can form thin, rotating disks and complex, visible structures. Dark matter, by contrast, seems not to shed energy in the same efficient way. It forms a broad halo rather than a luminous, thin disk. It shapes the galaxy gravitationally, but it does not participate in the ordinary choreography of light and cooling and atomic chemistry. This makes dark matter frustrating in a very specific scientific sense. It is not hidden because it is rare. It is hidden because its main known interaction with the visible universe seems to be gravity. And gravity is both universal and weak when measured at the scale of particle experiments. On cosmic scales, gravity dominates structure. In the laboratory, it is far too feeble to provide an easy detection route for individual particles. So the very thing that makes dark matter obvious in astronomy makes it maddeningly elusive in particle physics. Still, the evidence for its existence has become too broad to ignore. We have already spoken about galactic rotation curves and galaxy clusters, but it is worth dwelling on why these observations carry so much weight. In a spiral galaxy, stars at large distances from the centre move too quickly if only visible matter is present. In clusters, the motions of galaxies and the temperature of hot gas imply much more mass than what shines. Gravitational lensing reveals matter distributions extending well beyond luminous components. The cosmic microwave background indicates that ordinary matter is only a small fraction of the total cosmic content needed to explain the pattern of early density fluctuations. Large-scale structure grows in a way that is much easier to explain if some matter began clumping gravitationally without being tightly coupled to radiation in the early universe. Each of these arguments has its own assumptions, but they point in the same direction. That convergence is why dark matter now occupies such a central position in cosmology. It is not merely a convenient patch. It is the backbone of the current large-scale picture. And yet, even with all of that evidence, dark matter remains curiously undefined at the microscopic level. We know quite a lot about what it is not. or at least what it probably is not. It is not made mostly of ordinary atoms hiding in familiar forms. It is not just dim stars or cold gas. It does not seem to interact strongly with light. It cannot be too hot in the sense of moving too rapidly in the early universe, because then it would wash out the small-scale structures we observe later. It must be stable over cosmic timescales, or at least long-lived enough to survive from the early universe until now. It must carry mass. It must gravitate. Beyond that, the space of possibilities opens considerably. For many years, a leading idea was that dark matter might consist of weakly interacting massive particles. The appeal of this class of candidates was partly aesthetic and partly practical. Such particles could naturally have the right relic abundance under plausible early universe conditions, and they often appeared in extensions of the standard model, motivated by independent theoretical concerns. For a while, this seemed like the neatest path forward. Perhaps dark matter would be one new particle species with a mass and interaction strength that made it difficult, but not impossible to detect directly. That expectation shaped a huge amount of experimental work. Underground detectors were built to wait for rare collisions between dark matter particles and atomic nuclei. Telescopes searched for indirect signatures of dark matter annihilation or decay. Colliders looked for events in which missing energy might hint that dark matter had been produced and escaped undetected. These were not speculative side projects. They became major efforts across the field. So far, however, nature has not rewarded the simplest version of that hope. There have been interesting hints here and there, debated anomalies, changing exclusions, improving sensitivities, but no universally accepted direct detection of a dark matter particle. This does not mean dark matter is not particulate. It means the easy version of the story has not appeared. And when the easy version fails to arrive, physics does what it always does at its best. It broadens the search without giving up on rigor. That broadening is one reason dark matter has become tied so closely to the idea of a hidden sector. If dark matter is not just one isolated, weakly interacting particle, then perhaps it belongs to a richer set of particles that interact strongly among themselves and only weakly with ordinary matter. In that case, the reason we cannot see it directly is not merely that it is faint. It is that we are looking at only one side of a larger particle ecosystem. Before going that far, though, it helps to understand how a dark matter particle would behave in principle if one passed through you right now. The answer, in the most likely scenarios, is almost nothing noticeable at all. The Earth is thought to move through a halo of dark matter associated with the Milky Way. If dark matter is made of particles, then enormous numbers of them may be passing through our planet constantly. But because they interact so weakly with ordinary matter, they would slip through atoms, walls, oceans, and people, almost without effect. This is one of those facts that sounds dramatic until you remember that neutrinos do something similar all the time, and have been doing so with astonishing enthusiasm for a very long while. The difference is that neutrinos are part of the standard model, and can be produced and studied more directly, while dark matter remains stubbornly unidentified. In both cases, though, the lesson is that invisibility in physics often means weak interaction, not supernatural absence. Something can be entirely real and physically abundant while barely noticing the ordinary matter around it. That distinction also helps explain why dark matter is not usually expected to form ordinary structures such as stars, planets, or people. Ordinary matter can clump efficiently because it interacts electromagnetically. Gas clouds can radiate away energy, cool, and collapse into denser objects. Dark matter, if it lacks comparable dissipative mechanisms, mostly remains in diffuse halos. It contributes the gravitational scaffolding within which ordinary matter gathers, but it does not typically participate in the visible architecture built on that scaffolding. This picture has a surprisingly practical consequence for cosmology. Dark matter appears to have helped structure form early by providing gravitational wells that ordinary matter could later fall into once conditions allowed. Without that extra invisible component, the timeline for building galaxies from the tiny fluctuations seen in the early universe becomes much harder to reconcile with observations. In that sense, dark matter is not merely extra weight added after the fact. It may be one of the main reasons the large-scale universe looks the way it does. That is a remarkable role for something we have never seen directly. It is as though the invisible framework of a building turned out to matter more than the visible walls when explaining why the whole structure stands where it does. Still, scientific caution matters here. Dark matter is the leading framework because it explains a very broad set of data effectively, but physicists do not confuse explanatory success with finished identification. There remains a difference between saying something dark and gravitating exists and saying exactly which particle or particles make it up. That difference is what drives so much present research. Some experiments search for direct scattering in deep underground detectors shielded from ordinary background noise. The idea is simple in concept and painfully difficult in practice. If a dark matter particle occasionally collides with an atomic nucleus, the recoil might be measurable. The difficulty is that the expected signals are tiny, rare, and easily mimicked by other sources unless the apparatus is extremely clean and extremely sensitive. Other searches are indirect. If dark matter particles annihilate or decay under certain conditions, they might produce detectable byproducts such as gamma rays, charged particles, or neutrinos. Telescopes and observatories can look for unusual excesses from regions where dark matter is expected to be dense, such as the centers of galaxies or dwarf satellite galaxies. Here too the problem is interpretation. Astrophysical environments are messy. A curious signal may be a sign of new physics, or merely an ordinary process not modelled well enough. Collider searches take a different route. Rather than waiting for dark matter drifting through Earth, they try to create possible dark matter-related particles in high-energy collisions. Since dark matter would likely escape the detector, the signature is not a direct image but missing momentum, combined with visible particles recoiling against the unseen component. This is where CERN becomes especially important, because if dark matter connects to ordinary matter through some mediator, even a weak one, collisions at the Large Hadron Collider might produce traces of that connection. That possibility begins to shift the question. At first, dark matter was a cosmological necessity. Then it became a particle physics target. Now, in many theories, it becomes the gateway to a broader hidden structure. Perhaps what CERN can reveal is not dark matter itself in the simplest sense, but the portal through which the visible and dark sectors communicate. A dark photon, a hidden scalar, a long-lived mediator, a rare decay pathway, some slight but persistent distortion in the expected products of high-energy collisions. The visible world may not show us the dark world directly, but it might reveal the handshake between them. This is part of why dark matter remains such a strong scientific idea despite the absence of direct detection. The case for its gravitational role is already impressive. The open question is not whether the missing mass problem deserves attention. The open question is how the responsible physics is organized. Is dark matter one stable particle species and nothing more? Is it part of a hidden sector with its own internal complexity? Does it interact through a new force? Is there a light mediator that ordinary detectors have only barely begun to probe? These are not decorative questions. They determine how the early universe evolved, how structure formed, what signals experiments should seek, and how the standard model must be extended. There is also something humbling about the entire subject. Human beings first learned about matter through direct contact. We touch objects, see them, move them, heat them, break them, combine them. Then science widened that ordinary experience into chemistry, atomic theory, nuclear physics, and quantum fields. At each stage, matter remained something that could in some way be made visible through interaction. Dark matter breaks that habit. It forces us to accept that most matter may belong to a category that barely acknowledges the visible world except through gravity. Not absent, not imaginary, not unreachable forever, but quiet in a way ordinary matter is not. That quietness is why the subject sits at the crossroads of cosmology and particle physics so naturally. Astronomy tells us the shadow is there. Particle physics is trying to learn what casts it. And the more carefully physicists think about that shadow, the less likely it seems that the answer will be embarrassingly simple. Dark matter may not be a lone invisible particle drifting through a mostly ordinary universe. It may be evidence that ordinary matter is itself the minority component of a larger particle reality, one that has remained hidden because its strongest interactions do not involve us very much. That possibility is exactly what makes the search at CERN so tense. If the collider data are beginning to hint at hidden mediators or dark sector states, then dark matter stops being only a cosmic shadow and starts becoming the first visible edge of an entire unseen world. To understand why CERN is such a natural place to test that possibility, we need to move from the sky to the machine itself, from cosmic evidence to the controlled violence of high-energy collisions, where physicists try to force nature into revealing whatever it has managed to keep concealed. Once dark matter becomes a serious particle physics problem rather than only a cosmological one, the role of CERN starts to make much more sense. It is easy to describe the Large Hadron Collider as a machine for smashing particles together, and that description is not wrong. But it is also a little like describing a library as a building where paper sits quietly on shelves. Technically true, but not quite enough to explain why people built it. CERN keeps driving particles into each other at enormous energies, because high-energy collisions are one of the few ways we know to test whether the visible particles in the standard model are all there is, or whether nature has been keeping additional ingredients just beyond the reach of ordinary experience. The important word there is ordinary. The world around us feels stable, because most of the particles and interactions that matter in daily life sit at relatively low energies. At room temperature, in air, in stone, in bodies, in stars outside their most violent interiors, nature is not constantly producing exotic heavy particles. Those states are either too unstable, too massive, or too difficult to generate under normal conditions. If there are hidden particles that couple weakly to ordinary matter, then everyday environments may never reveal them clearly. The universe can contain them without making them obvious to us. That means if we want to expose new physics, we often need to create conditions that are not common in ordinary life but were common in the early universe, when everything was denser, hotter, and more energetic. That is one of the main ideas behind collider physics. A particle accelerator does not simply break matter apart. It recreates very high energy conditions in a controlled way, so that unfamiliar particles can be produced for brief moments and then studied through their decay products or their missing signatures. This is the crucial point. At very high energies, mass can appear in forms that do not normally exist around us. If a hidden particle can be produced at all, through interactions accessible to the visible sector, then collisions at CERN may generate it, even if only rarely and even if it survives only for a tiny fraction of a second before turning into something else. This is why the collider is not just a hammer, it is a translator between theory and reality. Theories propose that under the right conditions certain particles should exist. The collider provides those conditions often enough, and with enough precision that the predictions can be checked. If the particle is there and couples to the standard model strongly enough, then some trace of it ought to appear. If nothing appears where a model says something should, then the model begins to lose ground. The machine is violent, yes, but the purpose is disciplined. It is a way of asking nature a very direct question. What happens if we push matter into a regime where the known rules may no longer be the whole story? The reason this becomes especially important for dark sector ideas is that the dark sector, by definition, is not expected to advertise itself openly. If hidden particles have little or no electromagnetic interaction, telescopes will not simply photograph them. If they pass through ordinary matter almost without effect, laboratory detectors will not catch them easily by waiting around in the dark and hoping for a friendly introduction. So physicists look for portals, for ways the visible world and the hidden world might still talk to each other. A collider is one of the best places to search for those conversations because it gives us a chance to create the mediator itself, the bridge particle, the short-lived messenger that links known matter to hidden states. To understand why smashing particles helps, it is worth taking a closer look at what a proton collision actually is. A proton is not a neat little solid bead. It is a buzzing quantum object made of quarks, gluons, and an entire seething cloud of internal activity. When two protons collide at high energy, the collision is really a set of interactions among their constituent parts. Depending on how the energy is distributed, different outcomes become possible. Sometimes familiar particles are produced. Sometimes unstable heavy states appear and decay almost immediately. Sometimes energy leaves the detector carried by particles that interact very weakly, such as neutrinos. And, in theories beyond the standard model, sometimes the collision may produce something new that either decays in an unusual pattern or escapes in a way that creates an imbalance in what the detector records. That last point is one of the most important. Physicists do not always expect to see a hidden particle directly. Very often they expect to infer it from what is missing, delayed, displaced, or statistically excessive. A collision occurs, visible particles fly out, and the total pattern does not quite balance in the way the standard model predicts. There is momentum apparently carried away by something unseen. There is a cluster of tracks that begins not at the collision point itself, but some measurable distance away, suggesting a particle lived long enough to travel before decaying. There is a narrow resonance in a distribution where no standard model process should create one. There is an event topology that appears more often than expected. These are the kinds of clues collider physics is built to detect. This explains why CERN keeps pushing toward higher energies and larger datasets. New physics may be rare. Hidden sector production may be suppressed. Mediators may couple only faintly. The machine therefore has to do two things at once. It has to reach energies high enough to create the relevant states, and it has to produce enough collisions that even rare outcomes have a chance to show themselves. One spectacular event is usually not enough. Particle physics lives by statistics. You look for patterns emerging above background noise, not for a single theatrical moment that settles the matter forever. Nature is not obliged to make new physics obvious, and lately it has seemed almost committed to making it subtle. That subtlety is one reason people sometimes misunderstand why CERN has to be so big. If you want to explore a frontier where new particles may be heavy, weakly coupled, or both, then you need scale. You need strong magnetic fields to steer beams, long tunnels to accelerate them, highly sensitive detectors to reconstruct the debris, and enormous computing infrastructure to sort through the resulting flood of data. The collider is not oversized because physicists enjoy dramatic construction projects, although I am sure some of them do appreciate a tunnel of impressive ambition. It is large because the problem demands it. To glimpse new microscopic structure, you often need macroscopic engineering on a heroic scale. There is also another reason high-energy collisions matter for hidden physics. The early universe was effectively the greatest particle physics experiment ever run. In its first moments, temperatures and energies were high enough that many particle species that no longer exist today, in ordinary conditions, could have been produced abundantly. If dark matter or hidden sector particles were born in that early environment, then recreating similar energy scales in the laboratory is one of the only direct ways to test those ideas. CERN, in that sense, is not trying to imitate a modern astronomical object. It is trying to imitate, in tiny controlled flashes, the conditions that were common when the universe was young enough to be chemically useless and physically very exciting. That connection between collider physics and cosmology is one of the most elegant features of the whole field. A machine under the French-Swiss border is being used to investigate questions raised by galaxies, clusters, and the cosmic microwave background. The sky tells us there is missing matter. The collider asks whether the missing matter, or the particles connected to it, can be produced here on Earth. It is a remarkable chain of reasoning when you stop to think about it. Humans looked up at rotating galaxies, concluded that invisible matter must exist, and then built a vast underground instrument to hurl protons together in the hope that the invisible sector might momentarily reveal its passport. This is also why the Standard Model and collider searches are so tightly linked. The Standard Model tells us what should happen in ordinary high-energy collisions if only known particles are involved. That gives physicists a baseline. They know the expected production rates of many processes, the shapes of backgrounds, the signatures of known decays. New physics enters the story by disturbing that baseline. It may add extra events in a given channel. It may modify branching patterns. It may produce unexpected invisible momentum. It may generate particles with unusual lifetimes. But none of this can be recognized unless the known physics is already understood in exhausting detail. In other words, the success of the Standard Model is not an obstacle to collider discovery. It is the platform that makes discovery possible, because without a precise standard there is no meaningful anomaly. There is something almost paradoxical about that. CERN looks for new physics by relying heavily on the old physics. The better the Standard Model works, the more sensitive the search becomes to anything that does not fit. That is why small anomalies can trigger such intense interest. A tiny deviation against a well-understood background may mean more than a dramatic-looking event in a messy, poorly modelled environment. This is one reason collider results are presented with such caution. Researchers know how easily statistical fluctuations, detector effects, or underestimated backgrounds can pretend to be new phenomena. They also know that genuine discoveries often begin by looking disappointingly modest. For dark sector searches, this cautious style becomes even more essential. A hidden sector may not produce a clean, bright signal like a textbook particle, with a single obvious decay. It may produce cascades, missing energy, displaced decays, lepton pairs from light mediators, or multiple pathways that depend sensitively on masses and couplings. That means physicists do not search in one way only, they search broadly. Some analyses target events with a visible particle recoiling against missing momentum, since that could indicate that invisible particles were produced. Some look for narrow resonances in pairs of leptons that might signal a dark photon. Some hunt for long-lived particles decaying away from the collision point, which would be a particularly striking sign that something beyond the Standard Model is taking an unusual route through the detector. Some experiments focus on lower mass or more weakly interacting possibilities that the main detectors might miss. That diversity of search strategies answers another common question, which is why CERN seems to keep searching even after not finding a dramatic beyond Standard Model signal quickly. The answer is that new physics does not owe us a simple shape. Earlier expectations often assumed that if hidden particles existed, they would appear in relatively direct ways. But as the simplest models came under pressure, the search expanded into more difficult territory. Lighter mediators, weaker couplings, rare decays, hidden valleys, compressed spectra, dark showers, and long-lived particles all became increasingly important possibilities. The machine kept smashing particles into the unknown because the unknown turned out not to be waiting in the most convenient place. There is a lesson in that. Scientific disappointment is often productive when it is specific enough. Not finding certain classes of particles does not mean the search failed. It means the map changed. Whole regions of parameter space become excluded. Some theoretical ideas become less attractive. Others gain urgency. Experimentalists refine techniques. Detectors are reanalyzed with new strategies. The absence of easy discoveries forces the field into deeper creativity. That is part of what has happened with dark sector thinking. As simple one-particle dark matter stories became harder to confirm, the idea of richer hidden structures became more compelling. CERN is especially well suited to test such structures because its detectors are not looking at the universe passively. They are recording controlled collisions with known inputs and reconstructing detailed outputs. That allows physicists to perform very particular tests. If a certain mediator exists in a certain mass range and couples in a certain way, then events of a certain kind should appear above background at a certain rate. If a hidden particle lives long enough to travel before decaying, then the detector geometry can help identify that behavior. If energy is being carried out by invisible states, then momentum conservation lets physicists infer that something escaped. A collider gives you levers, not perfect ones, but real ones. It is also worth remembering that CERN is not just one experiment. The Large Hadron Collider hosts multiple detectors and specialized collaborations, each optimized for different kinds of measurements. Some are built for broad discovery capability at the highest energies. Others focus on precision studies of particular particle species or kinematic regions. This matters because hidden sector physics might show up in more than one way. A heavy mediator might be easiest to notice in one detector. A low-mass hidden particle with unusual decay patterns might be better probed by another. A rare flavor process might offer indirect hints, where direct production remains elusive. The search is therefore less like waiting for one grand alarm bell and more like listening across several rooms for subtle changes in sound. Another point that often gets missed is that collider physics does not only search for dark matter by trying to make the dark matter particle itself. Sometimes the most accessible thing is the messenger. If there is a portal between the visible and hidden sectors, that portal may be easier to produce than the full dark matter population. A dark photon, for instance, could appear as a resonance in ordinary charged particle pairs if it mixes weakly with the familiar photon. A hidden scalar might show up in exotic decays of the Higgs. A long-lived mediator might leave delayed signatures. In such cases, CERN is not finding dark matter directly, but it is finding the plumbing that would allow dark matter to matter, and in many ways that is just as important, because once you identify the mediator, the larger hidden framework becomes experimentally accessible. This is where the atmosphere around certain hints can become charged very quickly. Physicists know that a new mediator would be much more than an extra particle. It would be evidence that the visible sector is not closed under itself. It would mean there is traffic, however faint, between our known particles and something else. That is why even tentative anomalies tied to rare decays or unexpected resonances can cause such intense behind-the-scenes discussion. Not because everyone believes immediately, but because everyone understands what a confirmed signal would imply. At the same time, collider searches are hard for reasons that have nothing to do with theory and everything to do with reality. Detectors are complicated instruments with finite resolution, immense data rates, and countless potential backgrounds. Protons are messy initial states. Rare standard model processes can mimic new physics. Statistical fluctuations happen, detector mismeasurements happen, selection choices can matter. Analysts therefore live in a constant tension between openness and skepticism. They want to be sensitive enough to catch the unexpected without fooling themselves into promoting noise. This is not glamorous, but it is one of the reasons particle physics remains trustworthy. The field has learned the hard way that excitement without discipline produces mostly embarrassment, and yet the discipline has not reduced the ambition. If anything, it has sharpened it. CERN keeps smashing particles because there is still no substitute for directly probing the high-energy frontier in the laboratory. Telescopes can tell us that something unseen shapes the universe. Underground detectors can wait for rare interactions. But colliders actively create new states if those states are kinematically available and connected to the visible world. That makes them indispensable. They do not answer every question, but without them an enormous class of questions about hidden particles and new forces would remain frustratingly underconstrained. So when people ask why CERN keeps pushing forward despite the difficulty, the answer is really that the alternative would be stranger. We have overwhelming reason to think the visible matter described by the standard model is not the full inventory of the cosmos. We have compelling reasons to suspect that new particles or new sectors may exist. We have a machine capable of reaching energies where such ingredients might appear. Under those conditions, not smashing particles would be the truly irrational choice. Which brings us to the most delicate part of the story. Once the collisions happen, and once the detectors have recorded more data than any human could ever inspect, event by event, the real challenge becomes learning how to listen for a hidden world that may be trying very hard not to speak above a whisper. That whisper is exactly the problem. Physicists are not trying to catch a hidden world that crashes through the detector waving its arms. They are trying to catch one that may pass through almost unnoticed, leaving behind only a slight imbalance, a delayed decay, a rare pair of particles in an unexpected place, or a pattern so subtle that it only becomes meaningful after millions or even billions of collisions have been examined with exhausting care. This is why the hunt for hidden particles is quiet. Not because the machines are quiet, because they absolutely are not in any meaningful engineering sense, but because the signals being sought are faint, indirect, and very easy to bury under ordinary physics. That distinction matters, because from the outside particle, physics can seem like a field built on dramatic moments. A new particle appears, the headlines arrive, and someone somewhere receives a level of public attention that makes them deeply uncomfortable. In reality, most of the work is patient and statistical. A hidden particle search usually does not begin with a striking event that makes everyone in the control room leap out of their chairs. It begins with a theoretical possibility, then a careful definition of what that possibility would look like in data, then years of work to understand which ordinary processes might imitate that appearance, and only then a slow accumulation of evidence that may or may not ever become convincing. It is less like hearing a gunshot in the dark and more like trying to decide whether a very distant clock is ticking behind three walls in a storm. That quietness comes directly from the physics. If hidden particles exist, then the whole point is that they do not interact with ordinary matter in the strong, familiar ways that standard model particles often do. They may be neutral, they may couple very weakly, they may be long-lived, they may decay into visible particles only rarely, they may escape the detector entirely. In some models they may not even be produced directly very often, but only through the decay of some other unusual state. So the search is built around absences and irregularities as much as presences, missing momentum, unexpected lifetimes, strange decay topologies, slight excesses over background, a resonance too narrow or in the wrong place, a rate a little too high, a pattern a little too structured. One of the most important ideas in this hunt is that a hidden particle may announce itself not by where it appears, but by where it appears late. In ordinary high-energy collisions, many unstable particles decay almost immediately, and their products point back neatly to the collision point. That is the standard picture. But if a new particle is long-lived on detector scales, even by a tiny fraction of a second, it might travel a measurable distance before decaying. When that happens, the tracks from its decay products seem to begin not at the original collision, but somewhere displaced from it. This is called a displaced vertex, and it is one of the most intriguing signatures in collider physics, because it is both unusual and relatively hard for ordinary processes to fake in exactly the same way. A displaced decay is the sort of thing that makes experimentalists very interested very quickly, but not careless. There are always backgrounds to consider. Particles in the detector material can scatter in confusing ways. Certain known hadrons live long enough to travel small distances. Reconstruction software can occasionally be misled by complex events. So even a beautiful displaced signature does not become new physics merely because it looks unusual. It has to survive every boring explanation first. This is part of what makes the quiet hunt so demanding. The most exciting possibility is always forced to stand in line behind the most mundane one. Then there is missing energy, or more precisely missing momentum in the plane relevant to collider analysis. Since the total initial momentum in certain directions is known well enough, physicists can infer when something has left the collision without depositing visible signals in the detector. The standard model already gives one familiar cause for this, namely neutrinos. They are neutral, weakly interacting, and capable of carrying away momentum invisibly. So invisible momentum by itself is not a discovery, it is a clue. The challenge is to find event classes where the amount, distribution, or associated visible particles do not match the expected standard model sources. If a hidden particle is produced and escapes, it could create exactly this kind of imbalance. That sounds simple when said quickly, but in practice it is one of the most difficult forms of evidence to interpret. Detector resolution matters. Jets of hadrons are messy. A small mismeasurement can mimic missing momentum. Rare standard model processes can do the same. Events with neutrinos are common enough in certain channels to provide substantial background. This means physicists have to reconstruct collisions with extraordinary precision and understand the detector response in painful detail before they can say whether an unusual invisible signature means anything new. The hunt remains quiet because nature has given plausible ordinary explanations for almost everything, and each one has to be exhausted before the extraordinary option earns attention. This is also why hidden particle searches often rely on combinations of clues rather than a single dramatic feature. An event with missing momentum and a single recoiling photon might fit one class of models. A displaced decay producing a pair of leptons might fit another. A rare decay of a known particle into an unexpected final state might point toward a light mediator. A Higgs boson decaying in a way that standard model calculations do not predict could open another route entirely. The field does not search for the dark sector in one universal manner, because there is no reason to think the dark sector, if it exists, has chosen one convenient method of introduction. In fact, one of the most significant shifts in recent years has been the growing appreciation that new physics may live in corners. The original search strategies did not emphasize strongly enough. Earlier collider thinking often focused on prompt, energetic, easy to reconstruct signals. That made sense. If new heavy particles existed at accessible energies and decayed into visible standard model states quickly, then those signatures would be among the clearest. But as those searches repeatedly came up empty in their simplest forms, attention broadened. Physicists began taking long-lived particles more seriously. They paid more attention to low-mass mediators that might slip under the radar of standard triggers. They examined exotic Higgs decays, rare flavor processes, hidden showers, and unusual event geometries that do not fit the most traditional templates. This broadening was not an act of desperation, it was a sign of maturity. The field learned that nature may not be obliged to present new physics in the form most convenient for a first-generation search. Hidden particles, especially those belonging to a dark sector, may be difficult not because they are absent, but because they live in regions of parameter space where ordinary analyses are less sensitive. Couplings may be tiny, masses may be low enough or high enough to complicate detection, lifetimes may place decays in awkward regions of the detector, signals may be spread across many channels rather than concentrated in one. The quiet hunt is therefore as much about learning how to listen better as it is about waiting for nature to speak louder. That improvement in listening happens at several levels at once. There is the detector level, where engineers and experimental physicists work to improve timing resolution, tracking precision, calorimetry, and trigger systems. There is the analysis level, where researchers invent better ways to separate signal from background, often using increasingly sophisticated statistical and computational tools. There is the theoretical level, where model builders try to map out what hidden particles could reasonably do without violating existing constraints. And there is the strategic level, where collaborations decide which rare or unconventional signatures deserve dedicated attention, even when they do not fit the historical center of the field. The trigger system is an especially revealing part of this story. At the Large Hadron Collider, proton bunches cross with enormous frequency, producing far more events than can possibly be stored in full. So the detectors need trigger systems, layers of rapid decision-making that determine which events are interesting enough to keep for further analysis. This sounds like a purely technical matter, but it has deep implications for hidden particle searches. If your trigger is designed mainly to keep the most energetic and familiar-looking events, then soft, delayed or unusual signals may be thrown away before anyone ever studies them. That means the quiet hunt is not only about analysing what was recorded, it is also about making sure the right strange events are allowed into the record in the first place. This challenge has shaped a great deal of modern work. Search teams ask not just what a hidden particle would look like in theory, but whether the detector and trigger system would even notice it under real operational conditions. A long-lived particle decaying far from the interaction point might leave a signature that standard triggers were not optimized for. A low-mass dark photon might produce leptons that are too close together or too soft for some conventional selections. A hidden sector cascade might look like a diffuse oddity rather than a neat high-energy object. Designing searches around such possibilities requires a mindset that is both cautious and imaginative. You must respect the detector as it is, while also refusing to let its original assumptions define the limits of what can be found. There is something almost forensic about this work. Experimentalists examine the aftermath of collisions the way investigators examine the aftermath of an event with incomplete witnesses. They reconstruct tracks, cluster energy deposits, match timing information, estimate backgrounds, and ask which stories are consistent with what the detector saw. A hidden particle is not a visible object in the usual sense. It is an explanation competing with other explanations. To win, it must account for the data better than known physics and instrumental effects do. That is why even tantalizing hints lead first to skepticism rather than celebration. A serious collaboration is trained to distrust excitement until the ordinary possibilities have been dismantled piece by piece. This discipline is especially important because the standard model is so productive. It generates an enormous variety of signals, many of them complicated. Quantum chromodynamics alone can create events messy enough to test anyone's patience. Heavy flavor decays can mimic displaced structures. Electroweak processes can produce missing momentum through neutrinos. Rare combinations of known particles can accidentally populate odd kinematic regions. Detector noise, pile-up from multiple collisions and reconstruction ambiguities all add their own complications. Hidden particle searches therefore live in an uncomfortable truth. The universe contains both genuine mystery and abundant clutter, and telling them apart is the whole game. Still, that clutter has not stopped the search from becoming more ambitious. One reason is that hidden sector models often offer several distinct experimental handles. A dark photon might show up as a narrow resonance in pairs of electrons or muons. A hidden scalar could emerge in unusual decays of heavier particles. A portal interaction might reveal itself through events with invisible momentum, plus an ordinary visible object recoiling against it. Long-lived states could decay in the tracker, in the calorimeters, in outer detector regions, or even beyond the main detector volume. Some hidden particles might be light and numerous, producing unusual sprays of low-energy particles rather than one clean heavy object. Others might couple preferentially to heavy flavors, making rare decays of mesons a valuable hunting ground. This is why the search has spread across different experiments and detector concepts. The largest general-purpose detectors are powerful, but they are not the whole story. Some experiments are especially good at studying rare decays and flavor physics, where small deviations can signal virtual contributions from new particles, even if those particles are not produced on shell in large numbers. Others are being designed or adapted to catch long-lived particles that travel far from the interaction point before decaying. There are proposals and operating experiments aimed at the forward direction, where light weakly interacting states might appear. There are fixed target style approaches and beam dump inspired ideas in which hidden particles could be produced and then decay downstream in quieter environments. The quiet hunt is no longer one search in one room. It is a network of searches tuned to different ways the hidden world might leak into ours. That broader strategy reflects a deeper lesson from the history of physics. When nature is subtle, the correct response is not to shout louder at the same observable. It is to diversify the questions, Hidden particles may not reveal themselves where the earliest expectations placed them. They may be in flavor physics, in exotic Higgs decays, in long-lived signatures, in low-mass mediator searches, in precision anomalies, or in combinations of all these. The field has become increasingly comfortable with that complexity. A hidden sector, if real, may not have one front door. It may have several poorly marked side entrances, each opening only a little. The theoretical side of the hunt has also changed in a useful way. Early beyond standard model work often aimed for large, elegant frameworks that solved many problems at once. There is still value in that ambition, but hidden sector research has encouraged a more modular style as well. Rather than insisting on one grand final theory immediately, physicists often work with portal frameworks and simplified models. They ask what kinds of mediators can connect visible and dark sectors. They study how those mediators would affect production rates, lifetimes, and decay channels. They map constraints from cosmology, astrophysics, beam experiments, colliders, and precision measurements. This approach is practical. It allows theory and experiment to meet in testable slices, rather than waiting for a complete theory of everything to arrive fully dressed and unreasonably confident. There is a psychological adjustment embedded in that shift. The quiet hunt has made physicists more willing to treat faint possibilities seriously without overselling them. A small anomaly may matter. A null result may matter too. Exclusions reshape theory. Hints motivate new search strategies. The process becomes less about one decisive discovery moment and more about gradually carving the space of possibilities into a smaller and more informative shape. That can seem less glamorous from the outside, but it's often how real progress works when the object of study is elusive. And elusive is exactly the right word. Hidden particles are not just difficult because they are unfamiliar. They are difficult because the universe may have arranged their properties to make them rare in our detectors, while still cosmologically important. A mediator can be feebly coupled and yet crucial for the early thermal history of the dark sector. A long-lived state can evade conventional searches and yet dominate the phenomenology of an entire model. A low-mass particle can be produced often, but leave signatures that blend into backgrounds unless searched for with unusual care. The quiet hunt is therefore not a matter of waiting for stronger signals. It is a matter of understanding how weak signals can still encode deep structure. That is why patience has become one of the defining virtues of this part of physics. Not passive patience, not the kind where nothing happens and everyone simply hopes the next run will be kinder, but active patience. Analysts reprocess datasets with new selections. Detector experts improve reconstruction for non-standard topologies. Theorists reinterpret old results in the language of newer models. Collaborations publish dedicated searches for signatures that were barely considered a decade earlier. Null results are translated into exclusions on masses, couplings, and lifetimes. Step by step, the invisible becomes less unconstrained even before it becomes visible in any satisfying sense. This can feel a little frustrating when described in plain language. People understandably want to know whether the hidden particle has been found or not. Science, unfortunately, often answers that sort of question by first producing a long and extremely serious document explaining 18 reasons why the answer is still maybe. But that maybe is not empty. It is structured, it is narrowed by data, and each narrowing matters because hidden sectors are not infinite fantasies. They are physical proposals with consequences. The more carefully the hunt proceeds, the fewer hiding places remain that are both experimentally allowed and cosmologically useful. There is also something quietly reassuring in the fact that the field has become more comfortable with unusual signatures. It means physicists are no longer assuming that the new world, if it exists, must resemble the old one closely enough to be discovered by inherited habits alone. They are adapting the search to the possibility that a hidden sector really is hidden in form as well as content. That adaptation is one reason current hints at CERN, whenever they appear, can generate so much attention. A resonance, a rare decay irregularity, a displaced signal, an excess in a previously neglected channel. None of these is enough by itself, but each belongs to a landscape where the tools for hearing whispers have become much sharper, and once those tools are in place, the next natural question becomes unavoidable. If a hidden sector does communicate with our own, then through what kind of messenger does it do so? What is the particle or interaction that allows a shadow world to leave even the faintest trace in visible matter? That is where the discussion turns from the search itself to one of its most intriguing suspects, the idea that there may be a dark version of one of nature's most familiar messengers, and with it, a new force that has been slipping past us almost unnoticed. By the time physicists start talking about dark photons, many people understandably begin to suspect that particle physics may have wandered a little too close to science fiction and has perhaps decided not to come back for lunch. The name does not help. Dark photon sounds less like a careful theoretical proposal and more like something that would emerge from a machine in a film shortly before the city lights go out and everyone regrets funding the project. But the idea itself is not wild in that way. In fact, one reason it attracts so much attention is that it is strangely economical. It's one of the cleanest ways to imagine how a hidden sector could exist without constantly wrecking the standard model. A dark photon is, in the simplest description, a new force carrier associated with a hidden sector, one that can communicate with our visible world through a very small amount of mixing with the ordinary photon. That is why it matters so much. It is not just another speculative particle. It is a candidate messenger between two sectors of reality that may otherwise hardly notice each other at all. The reason this is considered elegant is that physics often likes symmetries, and the ordinary photon already teaches us what a force carrier can do. Electromagnetism works through a gauge symmetry in its mediator, the photon. So if a hidden sector has its own version of such a symmetry, then a corresponding force carrier is not an absurd embellishment. It is a very natural possibility. The dark photon would arise from the hidden symmetry structure of that sector, and in the simplest picture, it would remain invisible to ordinary matter except for a faint bridge to the visible photon. That tiny bridge is what makes the whole idea testable. Without it, the hidden sector could remain almost entirely sealed off from us, relevant only through gravity. With it, rare production and decay channels become possible in experiments, and suddenly, the hidden world is no longer completely silent. This is where the phrase secret force becomes useful, because the dark photon is not interesting merely as a lonely extra particle. It is interesting because it suggests the existence of a whole interaction that may operate among dark sector particles themselves. In other words, the hidden world may not be a cold storage room containing one inert relic. It may have its own internal dynamics. Dark matter particles could interact with one another through this dark force, much as charged particles interact through electromagnetism in our sector. That changes the story immediately. Once there is a force, there can be scattering, bound states, mediator decays, thermal histories, production channels, and perhaps even whole families of hidden particles shaped by the new interaction. The discovery of a dark photon would therefore not simply add one new name to the particle chart. It would imply that the visible world is not the only place where forces organize matter. That is why the idea is both elegant and troublesome. It is elegant because it adds only a small conceptual step, and yet opens a huge new territory. It is troublesome because once you allow one such portal, the rest of the hidden sector no longer has any reason to remain simple. Experimentalists at CMS explicitly describe the landscape in terms of both simplified dark sectors with a single mediator and extended dark sectors with more complicated structures, including hidden valleys, dark Higgs bosons, and other mediator possibilities. The search categories already reflect this. Some signatures are invisible, where the hidden states escape. Some are prompt and visible, where a mediator decays quickly into known particles. Others are long-lived, where the new state travels before decaying and forces the detector teams to invent special reconstruction techniques. The very vocabulary of the search tells you that physicists are no longer assuming one neat missing particle and nothing else. Now, the most important part of the dark photon idea is the portal itself. The reason it remains experimentally accessible is that the hidden mediator can mix faintly with the ordinary photon. That means it can sometimes be produced in collisions involving standard model particles, and can sometimes decay back into ordinary matter. This is a small effect by design, because if it were large we probably would have seen it already in a very obvious way. But small is enough. Small means a narrow resonance in a pair of leptons, or a rare decay chain, or an invisible imbalance if the dark photon leads to hidden states that escape detection. Small means the bridge exists even if traffic across it is sparse, and sparse traffic, in particle physics, is still traffic. One can think of the ordinary photon and the dark photon as belonging to neighbouring administrative departments of the universe that have, for some reason, agreed to share a tiny amount of paperwork. Not enough to merge offices, certainly, but enough that messages can occasionally be misrouted in a scientifically useful way. That's a silly image, but it captures the practical consequence. The visible and dark sectors do not need to couple strongly. They only need a small mixing that allows one to borrow a little of the other's accessibility. Then suddenly a particle from the hidden sector can leave faint footprints in ordinary detectors. It is precisely because the coupling is expected to be tiny that the idea avoids immediate conflict with the overwhelming success of the standard model. It slips through the cracks rather than smashing them open. This has made dark photons one of the most studied portal candidates at CERN and beyond. The NA64 experiment, for example, was built specifically to hunt for dark photons by looking for missing energy signatures in a controlled beam environment. CERN described the experiment from the outset as a search for a particle that might act as a bridge to the invisible dark sector, using energy conservation as the key principle. At the Large Hadron Collider, Atlas has searched for Higgs decays involving a photon and a dark photon, where the dark photon would appear through missing transverse energy, and CMS has carried out long-lived dark photon searches in which the mediator would travel a measurable distance before decaying into displaced muons. What makes these searches so revealing is not merely that they look for one hypothetical particle, it is that they probe different ways a hidden mediator might reveal itself, depending on its mass, lifetime, and coupling strength. And that last point is where the subject becomes especially interesting. A dark photon is not guaranteed to behave in one tidy way. If the coupling to ordinary matter is relatively stronger, then decays may be prompt enough to appear near the collision point, perhaps as a resonance in known particles. If the coupling is weaker, the dark photon may live longer and decay farther out, producing displaced signatures that require specialized triggers and tracking methods. CMS has emphasized exactly this challenge in its run-through searches, where improved trigger algorithms for displaced muons were crucial because long-lived particles can otherwise escape standard data selection. In other words, the same basic mediator concept can produce very different experimental personalities. It may show up like a punctual guest or like someone who appears late through a side door and still changes the whole evening. Once physicists became comfortable with that, the dark photon stopped looking like an isolated curiosity and started looking like the front edge of a much wider class of portal physics. If one hidden force carrier can communicate with the visible sector, then perhaps other messengers can as well. This is why the field also talks about Higgs portals, neutrino portals, and axion-like portals. In each case the logic is similar. A known or plausible type of field provides a narrow connection between visible particles and hidden sector states. CMS explicitly frames its dark sector program in terms of many such mediator structures, not only vector mediators like dark photons, but also dark Higgs bosons and other possibilities within both simplified and extended sectors. The importance of the dark photon, then, is partly historical and partly conceptual. It is the cleanest example of how a hidden force can remain hidden without remaining irrelevant. But the phrase secret forces means something even broader than one portal. It points to the possibility that the dark sector may have self-interactions rich enough to create hidden analogues of familiar visible phenomena. This is where hidden valley models and dark strong force scenarios enter the picture. CMS has described models in which a mediator produces a shower of dark mesons inside a hidden valley, with the dark mesons later decaying back to ordinary matter through another hidden sector particle, analogous to the photon. In some cases, this can generate highly unusual, almost spherical sprays of many low-energy particles known as soft unclustered energy patterns. That matters because it breaks the old expectation that new physics must appear as a few sharp high-energy objects. A hidden sector with its own strong dynamics may look messy, delayed and unfamiliar, more like a strange weather system in the detector than a single neat resonance. This is the sort of development that keeps theorists happy in the way only a severe complication can. On the one hand, it is wonderful because it means the hidden sector could be physically rich and not merely decorative. On the other hand, it means the search problem gets much harder. Instead of looking for one extra bump, you may need to look for dark showers, semi-visible jets, displaced decays, mixed visible and invisible final states, and signatures that standard triggers were never originally built to prioritize. Atlas has highlighted exactly this by discussing searches for dark sector jets, where the hidden world may generate puzzling signatures that interact only very weakly with known matter, yet still leave distinctive patterns in the detector. This is what makes the theory elegant trouble. Every simple portal you add opens the possibility of a sector whose internal behavior becomes wonderfully inconvenient. There is also a cosmological consequence that makes these secret forces more than collider entertainment. If dark matter interacts through a dark photon or some related hidden mediator, then the early universe would have evolved differently from the simplest picture of one inert dark relic freezing out and minding its own business forever after. Self-interactions could alter the thermal history of the dark sector. Mediators could affect relic abundance calculations. Hidden sector decays could change what signals remain visible to us today. The dark matter problem would stop being merely a question of adding one stable particle and would become a question of reconstructing a parallel microphysics that helps shape cosmic history. That is why the discovery of a dark photon would reach far beyond one experimental result. It would push cosmology, astrophysics, and particle theory into a much more entangled conversation. And this is exactly why people in the field become both excited and uneasy when dark photon searches improve or when hidden sector anomalies flicker into view. A confirmed signal would not simply tell us that the standard model needs one amendment. It would tell us that the visible sector has a relationship, however faint, with something beyond itself. It would mean new symmetries, new mediator dynamics, and very likely a broader particle population. The standard model would remain correct where it has been tested, but it would no longer look like the nearly complete list of microscopic actors. It would look like one side of an exchange. That is a much bigger philosophical shift than adding, say, one more heavy resonance that behaves mostly like a familiar cousin. There is a good reason, then, why so much effort is spread across different experimental environments. The Large Hadron Collider looks for high-energy production and exotic decays. Beam experiments like NA64 look for feebly interacting particles through missing energy methods. Future projects such as SHIP are being designed specifically to target very feebly interacting hidden particles by using high-intensity beams and downstream detection of long-lived states. CERN has described SHIP as aiming to explore the hidden sector with sensitivity beyond existing experiments because the more particles one produces, the greater the chance of catching particles that interact almost not at all with ordinary matter. That broad strategy tells you something important. Physicists do not expect the secret force to introduce itself politely at one machine in one way. They are searching across the lifetime frontier, the intensity frontier, and the energy frontier because the mediator may hide differently, depending on how nature chose to set the couplings. All of this leads to a curious emotional state inside the subject. Dark photons are simple enough to explain in a sentence and complicated enough to rearrange half of modern particle physics if one is found. They are conservative in the sense that they use familiar field theory language, yet radical in the consequences they carry. They respect the standard model by coupling weakly enough not to have ruined it, and at the same time they threaten to demote it from a near-complete theory of matter to a local theory of visible matter only. That combination is why they are so irresistible. They are not wild because they are bizarre, they are wild because they are plausible, and then there are the other elegant troubles waiting nearby. Perhaps the mediator is not a dark photon but a hidden scalar coupled through the Higgs. Perhaps the dark sector contains a confining force and whole families of unstable hidden hadrons. Perhaps long-lived states are the real clue, and the portal has been slipping past standard triggers for years. Perhaps what looks like a dark matter question is really a messenger question, and once the messenger is found, the rest of the hidden world will begin to unfold around it. This is why the search has become broader, not narrower. The dark photon remains the cleanest example, but it may turn out to be only one dialect in a much larger hidden language. So when people speak about dark photons and secret forces with a mixture of excitement and professional caution, that tone is well earned. These ideas are not merely ornamental theory. They are concrete frameworks guiding real searches at Atlas, CMS, NA64, and future hidden particle experiments at CERN. They offer a testable way for the visible universe to connect to a sector that might otherwise remain known only through gravity. And because the coupling can be tiny, because the lifetimes can be long, and because the hidden sector may have its own internal complexity, the result is a deeply attractive sort of headache. The model is simple enough to write down, subtle enough to evade easy discovery, and consequential enough that confirming it would force physicists to rethink what matter and force really mean at the most fundamental level, which is exactly the sort of trouble the field claims not to want and secretly hopes to find. Once you allow the possibility of a dark photon or any other portal between visible matter and hidden matter, the whole subject changes shape. Up to that point, it is still possible to think of dark matter as a single missing ingredient, one extra particle that somehow escaped the standard model and now drifts through the cosmos doing little beyond adding gravitational weight. That picture is simple, and for a long time many people hoped some version of it would be correct, because simple pictures are easier to test and much kinder to conference schedules. But the moment you introduce the idea of a hidden force, or a mediator that links our particles to another set of particles, the situation becomes much larger. Dark matter stops looking like one lost item, and starts looking like evidence that ordinary matter may be only one sector of a broader physical reality. That is what physicists mean when they talk about a hidden world beside our own. They do not mean another universe in the science fiction sense. They do not mean an extra reality floating off in a mystical direction beyond the stars. They mean something much more specific and in some ways much stranger. They mean a collection of particles and possibly forces that occupy the same overall universe, obey the same broad physical framework, and yet interact so weakly with ordinary matter that they have remained almost entirely outside direct observation. Hidden does not mean elsewhere. It means nearby in the deepest possible sense, present in the same cosmos, perhaps even passing through the same regions of space, but nearly invisible because the channels through which we usually detect matter are not the channels through which this sector operates. That distinction is worth sitting with for a moment because it goes against everyday intuition. In ordinary life, things are hidden because they are behind something, under something, too small to notice, or not where we expected to look. In particle physics, a sector can be hidden not because it is far away, but because its strongest interactions are not with us. The visible world is visible because our matter participates in electromagnetism. Light is how we see. Light is how telescopes work. Light is how hot gas glows, how stars shine, how surfaces reflect, how atoms in detectors produce measurable signals. If another sector exists and does not share those electromagnetic couplings in the usual way, then it can remain present while being almost entirely absent from the forms of evidence we rely on most naturally. This is why the phrase beside our own is actually better than beyond our own. Beyond suggests distance, beside suggests coexistence. A hidden sector, in most serious theories, is not a separate stage. It is another cast on the same stage, one that mostly keeps to itself and only rarely exchanges lines with the visible actors. That is a very different picture from the older habit of imagining physics as a single list of particles arranged in one complete family. It suggests a universe that is layered rather than singular, where the familiar particles are not the whole population, but one neighbourhood in a much larger city. There is a practical reason this idea has become increasingly attractive. It solves a conceptual problem created by the Standard Model itself. The Standard Model is extremely successful in describing known visible matter, which means any new particles added to the theory cannot interact too strongly with the familiar ones, or they would already have disrupted measurements that agree beautifully with experiment. A hidden sector gets around this neatly. New particles can exist in abundance, even with rich internal dynamics, without spoiling the Standard Model where it already works, so long as the coupling between sectors is small enough. That means you can have a great deal of new physics without causing obvious chaos in the visible sector. In other words, a hidden world is one of the few ways nature could be dramatically richer than we thought, while still looking frustratingly ordinary in most of our measurements. The logic becomes even clearer if you stop thinking in terms of one additional particle and start thinking in terms of a sector. A sector can contain more than one kind of matter. It can contain stable particles, unstable particles, mediators, perhaps its own symmetry structure, perhaps its own equivalent of force-carrying particles. Some hidden sector particles might be heavy, some light. Some might decay back into ordinary matter if a portal exists, while others remain stable and contribute to dark matter. Some could be long-lived. Some might interact strongly among themselves but only faintly with us. Suddenly, the dark matter problem is no longer merely a question of naming one invisible object. It becomes a question of hidden microphysics. That is a much bigger intellectual shift than it first appears. Once you say hidden microphysics, you're saying there may be processes happening in the universe that are every bit as real as atomic physics and nuclear physics, but mostly inaccessible to direct electromagnetic observation. There may be histories of formation, decay, scattering, annihilation, freeze out or freeze in within the hidden sector that matter for cosmology, just as the visible sector history matters for stars and gas and galaxies. The early universe may not have been a single thermal story. It may have contained multiple sectors evolving in partial contact or drifting out of equilibrium with one another. The visible universe we describe in textbooks may be only one branch of a more complicated early cosmic environment. This is where the idea can start to feel uncomfortably expansive, because once you open the door to a hidden world, you have to ask how rich that world is allowed to be. Is it merely a sparse sector with one stable dark matter particle and one mediator? Is it an entire family of particles? Could it contain analogues of bound states? Could dark matter self-interact through hidden forces in a way that affects the structure of halos? Could there be unstable hidden particles that once populated the early universe and then decayed away, leaving only indirect traces in cosmological observables? Could some hidden states be produced at colliders, while others remain accessible only through astrophysical effects? These are not decorative questions. They are the natural consequences of taking the hidden sector idea seriously, rather than treating it as a label. It is important, though, not to let the imagination outrun the discipline. Physicists do not usually speak of hidden worlds because they have lost interest in evidence. They speak of them because evidence has forced them to consider frameworks larger than the simplest visible matter picture. Dark matter observations already imply that the standard model does not contain all matter. Hidden sector models go one step further and ask what structure that missing matter might plausibly have. The answer may be minimal. It may also be surprisingly rich. At the moment, we do not know. But the reason richer models are taken seriously is not that they are entertaining. It is that they are among the most consistent ways to add large amounts of new physics without contradicting what the standard model already gets right. There is also a subtle but important difference between saying hidden and saying parallel. The word parallel can mislead people into thinking of a duplicate version of our world, perhaps with hidden stars, hidden chemistry, hidden life, hidden newspapers full of very interesting mistakes. Physics is not claiming anything so dramatic. A hidden sector could be much simpler than the visible one. It might not form complex structures at all. It might not cool efficiently. It might never condense into anything like atoms or planets, because the necessary interaction patterns may not exist there. Or, in some theories, it might contain its own forms of bound states or composite objects. But even then one has to be careful. Similarity of language does not imply similarity of experience. Calling something a dark atom in theory does not mean there are dark kitchens and dark umbrellas and a dark version of someone misplacing both at once. It means that if there are hidden charged particles and hidden forces, then bound states may be mathematically possible. The cosmological and structural consequences then become matters for serious calculation, not for enthusiastic storytelling. Even this restrained possibility is enough to change how we think about matter itself. For most of scientific history, matter gradually became more unified as our theories improved. The diversity of objects around us reduced to combinations of atoms. Atoms reduced to nuclei and electrons. Nuclei reduced to quarks and gluons. Forces became field interactions. The overall movement was toward a common underlying language. A hidden sector does not reverse that, but it complicates it. It says that the underlying language may contain multiple dialects, some of which barely communicate with ours. The visible particles we know may not be the complete alphabet of matter, only the alphabet of one sector. That change has consequences for how we interpret astronomical observations as well. If hidden matter has its own interactions, then dark matter halos may not behave exactly like simple collections of non-interacting particles. Self-interactions could alter the inner structure of halos, the shapes of galaxies, or the behaviour of matter during cluster collisions. Different hidden sector models can therefore leave different cosmic fingerprints, even when none of the particles are seen directly. This is one reason the subject sits so naturally between particle physics and cosmology. You cannot understand a hidden world only from the collider side or only from the sky. The hidden sector, if it exists, influences both. And then there is the philosophical discomfort, which is not a technical term but deserves a place in the discussion anyway. A hidden world beside our own would mean that our ordinary sense of what counts as matter has been provincial all along. Not wrong exactly, but local. We would have spent centuries studying the visible sector in exquisite detail, eventually building the standard model, only to learn that this visible sector is not the general theory of matter, but the local theory of our matter. That is a much humbler conclusion. It is the particle physics version of discovering that the map one thought was of the whole country is in fact a very accurate map of a single district. And the hidden sector idea makes that humility operational. It does not merely say there are unknown things. It says there may be unknown things organised into a coherent framework. That coherence matters, because it means the hidden world is not a random pile of leftovers. It could have principles, interactions, production channels, thermal histories, and observable consequences. It could be physics in the full sense, not just missing mass. The early universe is where this possibility becomes especially powerful. In the first moments after the hot Big Bang, temperatures were high enough that particles could be produced abundantly, and interactions among sectors may have been much more important than they are today. If a hidden sector existed, then its population may have been set during this period, perhaps through thermal equilibrium with visible matter, perhaps through a much weaker process where hidden states were slowly fed from visible interactions, perhaps through decays of heavier particles. Different portal strengths would produce different cosmic histories. A strongly coupled hidden sector might once have been in significant contact with the visible one before decoupling. A feebly interacting hidden sector might never have equilibrated fully and instead accumulated its population gradually. These are very different scenarios, and they matter because they determine relic densities, decay products, cosmological bounds, and what experiments should search for today. So when physicists imagine a hidden world beside our own, they are not inventing a decorative extension of the standard model just to make the universe feel larger. They are trying to answer concrete questions. Why is dark matter there in the abundance we infer? Why has it been so hard to detect directly? Why do some portal models remain consistent with precision experiments? What signatures should appear at colliders or beam experiments if the visible and hidden sectors communicate? How might the structure of the hidden sector affect galaxy formation or small-scale halo behavior? The concept is large because the problem is large. There is also the matter of language, which in this subject can do more harm than good if handled lazily. Hidden world, dark sector, shadow particles, secret forces. All of these are useful shorthand, but they also risk making the idea sound more mystical than it really is. The underlying proposal is completely physical. The hidden sector, if real, would consist of fields and particles just like any other sector in modern theoretical physics. It would be described mathematically, constrained observationally, and tested experimentally. The darkness is not supernatural darkness. It is the practical darkness of weak coupling to the visible electromagnetic world. That is all, and that is already remarkable enough. In fact, one reason the idea has become respectable rather than fringe is precisely because it is so ordinary in theoretical structure. Hidden sectors arise naturally in many attempts to extend the standard model. Once you stop insisting that every field must couple strongly to visible matter, it becomes easy to write down sectors that are largely secluded. The real challenge is not inventing them. The real challenge is narrowing which ones are physically relevant and how they can be tested. That is why portal particles matter so much. They transform a hidden sector from a purely gravitational inference into an experimentally addressable possibility. If such a sector exists, the universe may contain entire interaction networks that almost never light up our instruments directly, yet still shape cosmic evolution. That thought has a way of changing even familiar questions. When we ask what matter is made of, we no longer mean only the matter in stars, rocks, and people. We mean all matter, including the kinds that may never form luminous structures but still dominate the gravitational budget of the cosmos. When we ask whether the standard model is complete, we no longer mean complete for atoms, we mean complete for reality. On that larger standard, the answer already appears to be no. It is also worth recognizing how modest the threshold for a major conceptual change would be. Physicists do not need to discover an entire hidden particle zoo all at once to take this seriously. One confirmed mediator would be enough to transform the subject. One robust portal signal would establish that visible matter is not isolated. One clear observation of a new long-lived particle connected to a hidden interaction would force the field to redraw its map. That is why the atmosphere around this topic can become so tense so quickly. The consequences are disproportionate to the apparent size of the signal. A small opening in the wall is enough to prove there is another room. This is also why the hidden world idea creates such a peculiar emotional mixture inside physics. It is exciting, obviously, because it offers a path beyond the standard model that is testable and rich. It is humbling because it implies that our familiar sector is not the full census of matter. It is frustrating because the couplings may be tiny, and the signals may be rare. And it is strangely orderly because the hidden sector idea is not a wild break from established physics, but a natural extension of how field theories already work. The universe would not be abandoning its logic. It would merely be revealing that the logic applies more broadly than we first realized. Seen in that light, the phrase, A hidden world beside our own stops sounding theatrical and starts sounding almost conservative. It is simply the statement that reality may contain additional sectors whose strongest interactions are not with us. Our instruments, which evolved historically around light and visible matter, would then be deeply biased toward one subset of what exists. Astronomy discovered that bias first through gravity. Collider physics is now trying to discover whether that bias can be overcome in the laboratory through rare portals, exotic decays, missing momentum, and long-lived particles. And once you accept that this is the real possibility on the table, you can also see why even very careful physicists start to feel uneasy when certain data begin to look suggestive. If the visible world is only part of the universe, and the hidden sector is beginning to leak into experiment, then every anomaly has to be treated with both skepticism and a certain amount of dread. Because a confirmed signal would not just add something new, it would reduce the standard model from a nearly complete picture of matter to a sector-specific one, and it would force physicists to confront how much of the universe may have been standing beside them all along without ever properly introducing itself. The word panicking needs a little translation before we can use it honestly. In ordinary language, panic means confusion, shouting, bad decisions, and perhaps somebody dropping a coffee in a way that becomes unfairly central to the memory of the day. In physics, panic is much quieter and much more disciplined. It looks like researchers reading the same plot 12 times in a row and finding new reasons to distrust it each time. It looks like a group chat becoming active at an hour when nobody should be that awake. It looks like a seminar question that is phrased politely, but lands with the force of a legal cross-examination. It looks like someone saying this is probably nothing, while already thinking through 3 ways it might change the field. That is the kind of panic this topic deserves, not theatrical fear, professional alarm. And the reason physicists react that way to possible dark sector hints is not because they are eager to be dramatic. It is because they understand exactly what a real signal would mean. A confirmed hidden sector result would not be just one more particle added to a long list. It would imply that visible matter is not a closed system. It would mean there are particles and possibly forces beyond the standard model that are not just mathematically convenient but physically present. It would mean the missing matter problem in cosmology has finally touched the laboratory in a way that cannot be ignored. It would mean whole classes of theories that used to feel optional suddenly become mandatory. And it would mean that decades of careful confidence in the near completeness of known particle physics would need to be revised into something humbler and much larger. That is why the panic is careful. Physicists know that if the result is real, the consequences are enormous. They also know that most suggestive results are not real in the final sense. This combination creates a very specific emotional atmosphere. They cannot dismiss the anomaly too quickly because the stakes are high. They cannot embrace it too quickly because the history of the field is full of signals that faded under better data, improved calibrations, or more patient analysis. So they enter a kind of suspended seriousness. Every assumption is checked, every background is questioned, every detector effect is reconsidered, every statistical treatment is re-examined. This is not lack of courage. It is what courage looks like in a field where false discovery is easy and genuine discovery is rare. There is a useful way to think about it. Particle physics is a science of tiny effects sitting inside enormous amounts of ordinary activity. The Large Hadron Collider produces an immense number of collisions, and most of them do exactly the sorts of things the standard model says they should do. Even rare standard model processes can still happen often enough to mimic something exotic if you are not careful. A detector may have subtle inefficiencies. A reconstruction algorithm may classify a complex event in a way that slightly biases the result. A background estimate may be just a little off in the most inconvenient region. A random statistical fluctuation may create a bump that looks far more persuasive than it has any right to look. All of these things are known to happen. So when a possible signal emerges, physicists do not ask first how exciting it is. They ask how many boring ways it could be lying. That habit can seem almost joyless from the outside, but it is actually the source of the field's credibility. Discoveries in particle physics matter precisely because the standards are so severe. Researchers have learned, sometimes painfully, that the universe is not the only thing capable of generating misleading patterns. Humans are good at seeing structure where none exists. Software is good at introducing tiny biases. Instruments are good at surprising the people who built them. Statistics is good at producing improbable events if you give it enough chances. So the professional response to a tempting anomaly is not celebration. It is interrogation. Still, the dark sector raises the tension to a different level, because it sits at the intersection of so many unresolved problems. Dark matter is already strongly supported by astronomical and cosmological evidence. The standard model is already known to be incomplete. Hidden sector theories are already plausible ways of explaining how new particles could exist without having spoiled previous measurements. So a hint in this area does not come out of nowhere. It plugs into a larger framework of expectation. That is why even a small anomaly in the right channel can make people nervous. It is not merely an oddity. It is an oddity with somewhere to go. Suppose, for instance, that an experiment sees an excess in a rare decay channel that could be interpreted as a light mediator, or a displaced signature that fits some class of long-lived hidden particle models, or a missing momentum pattern that seems difficult to reconcile with known backgrounds. None of these is enough on its own, not remotely, but each one activates a large amount of existing theoretical machinery. Suddenly theorists can write down models that fit the scale and coupling. Experimentalists can compare with earlier exclusions. Cosmologists can ask whether the same mediator could affect relic abundance or thermal history. Other collaborations can check whether their data ought to contain a related effect. The anomaly stops being isolated, it becomes connected, and connection is what makes people professionally uneasy. There is also the status problem, which is not about ego so much as intellectual structure. The standard model occupies a very high place in modern physics because it has earned that place. It is not a fragile theory looking for excuses to retire. It is a theory that has survived extraordinary experimental pressure. So whenever something appears that might point beyond it, physicists feel two conflicting obligations at once. One is the obligation to protect a theory that has repeatedly proven itself against weak or fashionable claims. The other is the obligation to follow the data wherever they lead, even if that means reducing the theory from a near-complete framework to a sector-specific approximation. Balancing those obligations is psychologically demanding. It means being loyal to the evidence more than to the elegance of what you already know. That is harder than it sounds. Scientists, like everyone else, build intellectual habits. They spend years learning what counts as plausible, what kinds of models deserve attention, what kinds of signatures usually turn out to be noise, what the known background processes tend to do, how detectors behave, which anomalies history has already taught them to distrust. Those habits are useful most of the time. But a genuine new discovery often enters through the same door as 100 previous disappointments. That means you need enough skepticism not to embarrass yourself, and enough openness not to miss the thing you've been waiting for. This is part of why the panic stays quiet. It is the sound of highly trained caution struggling with real possibility. The cultural memory of the field also matters. Particle physics has lived through many moments when something looks suggestive and then disappeared. A resonance appears in one dataset and fails to return. A flavor anomaly grows interesting and then weakens under improved analysis. A slight tension gains headlines and then slides back into statistical ordinariness. These episodes do not make physicists cynical exactly, but they do make them disciplined. No serious researcher wants to build a castle on a fluctuation. No collaboration wants to declare victory and then retract under the weight of more data. So when a hidden sector hint shows up, the first instinct is often to try to kill it. Not because they dislike discovery, but because a signal that survives active attempts to destroy it is far more valuable than one protected by wishful thinking. This is why replication matters so much. A truly important signal should not depend delicately on one binning choice, one fitting method, one detector subregion, one narrow dataset, or one analysis team. It should either grow stronger with more data, or at least remain stable under scrutiny. Related channels should be examined, alternative reconstruction methods should be tried, systematic uncertainties should be varied, control regions should be stressed, independent experiments should ask whether they see anything compatible. A genuine dark sector portal would likely leave more than one footprint. Perhaps not all at once, but enough that the overall picture begins to harden. Until that happens, panic remains contained inside conference rooms, internal notes, and unusually active email threads. Another reason the response is so intense is that hidden sector physics has a way of expanding the scope of any signal very quickly. If a heavy resonance were found that behaved like a straightforward extension of a familiar pattern, that would already be major news. But a hidden sector mediator is different. It implies structure beyond itself. A dark photon is not just a particle, it is evidence for a hidden interaction. A long-lived state consistent with a portal model is not just an odd decay. It is evidence that visible matter is coupled, however weakly, to an additional sector. This is why people panic carefully. The conceptual consequences are disproportionate to the apparent size of the first clue. Take the Higgs boson as a point of comparison. Its discovery was monumental, but it completed a long-expected piece of the standard model. A hidden sector signal would do the opposite. It would open a piece that many suspected existed, but that no established framework fully contains. Instead of closing a question, it would multiply questions. What is the full particle content of the hidden sector? How many mediators are there? Does the hidden force confine? Is dark matter part of the same sector? What does the early universe have to be recalculated to include? Which past null results now need reinterpretation? Which future detectors should be redesigned? This is not the sort of discovery you fit politely into the existing syllabus and move on from. It changes the syllabus. Then there is the matter of career time, which sounds mundane but is part of the emotional texture of the subject. Physicists can spend years, sometimes decades, working on analyses that probe tiny corners of possibility space. A strong hidden sector hint can suddenly make those corners central. People who are previously working on what seem like niche signatures may find themselves at the center of a major conversation. Others may realize that old datasets deserve new reinterpretation. Experimental priorities may shift. Funding arguments may change. Proposed detectors that once seemed specialized may suddenly look essential. The field has to reorganize not only its ideas, but also its practical attention. That sort of reorganization begins long before anything is confirmed, which is another reason even preliminary anomalies create pressure. And yet the professionalism remains because physicists know how badly things can go if excitement outruns proof. The public often encounters science through headlines that flatten uncertainty into declaration. Inside the field, the tone is different. A result may be called interesting, suggestive, tantalizing, worthy of follow-up, compatible with some models, mildly inconsistent with background-only expectations, or not yet significant enough for a strong claim. That language can sound painfully restrained to outsiders, but it serves a real function. It allows the field to think clearly while under emotional load. Saying this may be something important is easier to defend than saying we have found a hidden world and then explaining 6 months later that the hidden world was actually a trigger issue and a statistical bump that fell apart under reprocessing. There is also a deeper reason this particular subject produces anxiety. Dark sector physics threatens a cherished simplification. For a long time, even after dark matter became accepted as real in some form, it was still possible to imagine the solution as minimal. One new stable particle, perhaps. One extension that preserves most of our instincts. One neat repair. But hidden sector ideas make the universe larger in a more unruly way. They imply that the visible particles may not be the central cast after all. They imply that our matter is one local manifestation inside a richer particle reality. That is not merely a technical revision. It changes the narrative of fundamental physics, and narratives matter, even in very serious sciences. You can see this in how researchers talk when they are being candid with one another. There is often a strange mixture of hope and defensiveness. People want the signal to survive because a real break beyond the standard model would be historic. At the same time, they brace themselves for disappointment because experience has trained them to expect it. This creates a form of emotional compression. Interest rises. Public claims stay measured. Internal scrutiny intensifies. Nobody wants to be the person who ignored the first real sign of hidden physics. Nobody wants to be the person who overinterpreted noise. So the field lives, for a while, in between. In that in-between state, the details become everything. How stable is the excess under different event selections? Does the significance survive the look elsewhere effect? Are the control samples behaving as expected? Could the background model be underestimating a known process? Is there any detector region with suspicious behavior? Has the analysis been blinded properly? Are theorists fitting the anomaly by stretching parameters beyond what other constraints allow? Does another experiment have a compatible sensitivity? These are not bureaucratic questions. They are the actual substance of scientific decision-making when the stakes are high. Professional panic is a checklist with elevated heart rate. One especially interesting feature of dark sector hints is that they can force unusual collaborations between communities that do not always move at the same pace. Collider physicists focus on detector signatures, cross-checks, and event-level interpretation. Cosmologists think in relic densities, thermal histories, and large-scale structure. Astroparticle researchers think about direct detection and indirect signals. A promising mediator can link all three. Suddenly a result from one corner of physics has implications for several others. This is exciting, but it also increases the pressure. More communities begin examining the same possibility, and each brings its own constraints, instincts, and skepticism. A model that fits a collider anomaly may fail cosmology. A cosmologically attractive portal may be excluded by beam experiments. A direct detection null result may severely limit the coupling range. The panic becomes collective, but still professional. It is also worth noting that some of the strongest reactions do not come from spectacular anomalies, but from anomalies that seem almost annoyingly modest. A hidden sector is expected to couple weakly. That means the first real signal may look small, a narrow excess, a few displaced events, a branching ratio slightly off, a region of parameter space that stops looking comfortably excluded. These are not the sorts of things that make for cinematic storytelling, but they are exactly the sorts of things that could matter most. Physicists know this. They know that discovery does not always arrive wearing a spotlight. Sometimes it arrives as a statistical discomfort that refuses to go away, and that refusal is the key point. Panic becomes more serious when the hint persists. One run may show something odd, another run shows something compatible. A reanalysis doesn't kill it. A related search sees a whisper in the same neighbourhood. The confidence is still not enough for a claim, but the pattern begins to acquire memory. At that stage, the field becomes very tense indeed, because now the possible futures separate sharply. Either the signal will eventually collapse and everyone will feel a mixture of relief and annoyance, or it will strengthen, and physics will cross one of those rare thresholds after which the subject is no longer quite the same. That threshold matters because a confirmed dark sector signal would not be just another discovery. It would rearrange priorities across high-energy physics. Hidden particle experiments would gain urgency. Existing data sets would be mined again with new assumptions. Theoretical work on portal models and extended dark sectors would move from plausible speculation to essential interpretation. Cosmological models would be revisited. discussions of the standard model would change tone permanently. Even the language of what counts as ordinary matter would shift. Ordinary would come to mean visible sector matter, not matter in general. This is why physicists are panicking carefully and professionally. They are not panicking because they dislike uncertainty. They are panicking because they understand structure. They know how much of modern physics rests on the standard model being incomplete only in controlled, externally motivated ways. They know that dark matter has been waiting for a microscopic explanation for a very long time. They know that portal signals would connect laboratory data to cosmic missing mass in an extraordinarily powerful way. And they know that if the hidden sector is beginning to show itself, then the right response is neither denial nor premature celebration, but the most rigorous scrutiny the field can provide. There is something admirable about that response. The closer science gets to a potentially revolutionary result, the more conservative its internal behaviour often becomes. That is not cowardice. It is respect for the fact that reality only has to be discovered once, while mistakes can be made indefinitely. A hidden world beside our own, if real, will still be there after every cross-check. A false signal will not survive the same treatment. So the profession tightens its standards exactly when the imagination wants to run fastest. And perhaps that is the most human part of the story. Beneath all the detector language and statistical caution, there is a very old intellectual feeling at work. The sense that the world may be bigger than the version of it we have managed to explain so far. The sense that a familiar framework may be giving way at the edges. The sense that if the next anomaly survives, then we are no longer just polishing the known picture, but stepping across its boundary. Scientists do not usually call that fear, because fear is not a terribly useful term in a collaboration meeting. But a careful, professional form of panic is close enough. Because the possibility on the table is not just that one experiment found something odd. It is that the universe may finally be beginning to tell us how much of itself we have not yet been counting. If the dark sector is real, the first thing that gets bigger is not the collider program, or the list of particles, or the number of papers, though all of those would grow very quickly and with great enthusiasm. The first thing that gets bigger is the meaning of the word matter. Right now, in ordinary conversation and even in much of physics education, matter still tends to feel like a fairly unified idea. There is matter made of atoms. Atoms are made of nuclei and electrons. Nuclei are made of quarks held together by gluons. The standard model organises the elementary pieces and the forces that act on them. Even when that story is presented carefully with all the usual warnings about dark matter, neutrino mass, and the unfinished business of gravity, it still leaves many people with the impression that the visible particles are the main cast, and the unresolved issues are side cases around the edge. A real dark sector would destroy that comforting scale of importance almost overnight. It would tell us that visible matter is not the default form of matter in the universe at all. It is one form, our form, the form that builds stars, planets, chemistry, and all the instruments that allow us to ask scientific questions, but not the dominant form in the cosmic inventory. In practical terms, that would mean much of what we have called fundamental matter for the last century was fundamental only within the bright sector we happen to inhabit. It would not make the standard model wrong where it works. It would make it provincial. That is a much bigger change than people often appreciate at first. Scientific revolutions are not always about throwing away an old framework. Sometimes they are about reducing its territory. Newtonian mechanics still works for ordinary speeds and scales, but relativity and quantum mechanics showed that it was not the general story of motion and matter. A confirmed dark sector would do something similar to the standard model. It would remain one of the greatest theories ever built, still indispensable, still correct in the domain where it has been tested, but no longer defensible as anything close to a nearly complete census of microscopic reality. It would become the visible sector theory, not the theory of matter as such. That change would immediately force a reorganization of particle physics itself. At the moment, most extensions of the standard model are still discussed as extensions, as though one is adding rooms to a house whose main structure remains central. A real dark sector would suggest a different image. The visible sector would be one wing of a larger structure, and the hidden wing might not be small. It could contain stable particles, unstable particles, mediators, self-interactions, perhaps even dynamics that are as rich within that sector as the strong and electromagnetic interactions are within ours. The question would no longer be which single particle solves dark matter. The question would become how many sectors reality contains, how strongly they communicate, and whether the dark sector is itself simple or internally complicated. This is where everything begins to widen at once. Cosmology would widen first because the early universe would have to be retold. At present, the story of the early universe is already subtle. Physicists describe a hot, dense beginning, a rapid expansion history, particle interactions in thermal equilibrium, freeze-out processes, nucleosynthesis, the release of the cosmic microwave background, and the gradual growth of structure under gravity. That story is not casual. It has been shaped by decades of calculations and observations. But if the dark sector is real and experimentally accessible, then the early universe was not a one-sector thermal drama with one invisible extra ingredient added in the background. It may have been a multi-population environment in which visible matter and dark sector matter exchanged energy through portals, fell out of equilibrium at different times, and evolved in partially linked ways. That would matter because the relic abundance of dark matter depends on history. The amount of dark matter present today did not simply appear as a permanent cosmic fact. It was set by processes in the early universe. If there is a dark force, or multiple dark particles, or unstable mediators that once fed the hidden sector, then the abundance we see today could reflect an intricate history of production and depletion, not just one clean freeze-out calculation. Some hidden particles might have decayed away long ago, some may have remained stable, some may have helped maintain equilibrium within the hidden sector, even after the visible sector stopped talking to it efficiently. Once this becomes real rather than speculative, cosmology stops being a story of ordinary matter plus one dark correction and becomes a story of coupled sectors. That would also affect the way we understand structure formation. In the simplest picture, dark matter provides gravitational scaffolding, and ordinary matter falls into it later, eventually making galaxies and stars. That broad picture has been very successful, but if the dark sector has self-interactions, the detailed behavior of halos could change. Inner density profiles, the shapes of halos, the rates of small-scale merging, the behavior of matter in cluster collisions, and the evolution of dwarf galaxies might all need to be reconsidered in the light of hidden microphysics. Some long-standing tensions in small-scale structure could become easier to explain. Others might become sharper. Either way, the point is that the sky would stop being merely evidence for dark matter in general and start becoming a laboratory for dark sector properties. That would be a remarkable shift in scientific method. Astronomical surveys would no longer be used only to confirm that unseen matter exists. They would become tools for diagnosing how hidden matter interacts with itself. A halo profile would not just be a large-scale gravitational shape. It might be indirect evidence about mediator masses, interaction strengths, or scattering rates within a dark sector. Cluster collisions would no longer be simply spectacular confirmations that most mass is non-luminous. They could become constraints on hidden sector dynamics. The cosmic microwave background would still be a record of the early universe, but now it would also become a filter on how much the hidden and visible sectors could have communicated without disrupting known cosmological observables. In parallel, collider physics would get bigger in a different way. Right now, collider searches for hidden particles can still feel exploratory in the cautious sense. They are serious, but they operate in a world where the hidden sector remains hypothetical. If a real mediator were confirmed, that would change the logic of the whole enterprise. Searches would no longer be broad speculative sweeps through many possible signatures. They would become targeted investigations of a known portal into a real hidden sector. The immediate question would be what else is behind the first signal? If a dark photon were found, physicists would ask whether there are dark Higgs-like particles, whether the mediator decays invisibly into stable hidden states, whether there are heavier or lighter companions, whether the dark force confines, whether long-lived states are common, and whether the Higgs boson or other standard model particles have exotic decay channels into that sector. This means the interpretation of data would grow larger as well. Existing collider results would need to be reanalyzed under new assumptions. Null results that once seemed generic might suddenly become highly informative. Channels that were considered marginal could become central. Trigger strategies would be redesigned around confirmed hidden signatures. Entire detector upgrades would be justified in more precise terms. Experiments optimized for long-lived particles, weak couplings, or low-mass mediators would move from being promising side programs to essential parts of the field. It would not simply be a matter of collecting more data at the same machine. It would be a matter of rethinking what the machine is for. The same enlargement would affect direct detection and indirect detection. For years, many dark matter experiments have been framed around the hope that a stable dark matter particle occasionally scatters off ordinary matter or produces detectable annihilation or decay products. A confirmed dark sector would complicate both hopes and make them more interesting. Perhaps direct detection has been difficult not because dark matter barely interacts at all, but because the relevant mediator is light, or the coupling is highly structured, or the dominant dark matter state is part of a richer population than the simplest models assumed. Perhaps indirect signals have been hard to interpret because hidden sector cascades alter the final products before anything reaches visible detectors. Suddenly old null results might look less discouraging and more diagnostic. They would not tell us merely that dark matter is hard to find. They would help map which parts of the hidden sector are doing the talking and which are remaining silent. The meaning of simplicity would also change. For a long time, much of particle physics hoped for elegant minimal extensions. One new symmetry, one new particle family, one dominant dark matter candidate, one neat story. If the dark sector is real, elegance may still survive, but it will be a different kind of elegance. It will not be the elegance of one missing puzzle piece that snaps into place. It will be the elegance of realizing that the puzzle always had another region beyond the frame we first noticed. That kind of elegance is broader and less tidy. It asks physicists to accept that reality may be structured in a way that is coherent without being minimal in the human sense. That matters intellectually because the standard model has encouraged a certain expectation about successful theories. It is compact, predictive, mathematically disciplined, and experimentally extraordinary. A dark sector would not erase those virtues, but it might force us to accept a universe whose basic inventory is less economical than many hoped. There could be multiple sectors with different interaction strengths and different observational accessibility. There could be particles whose main significance is cosmological rather than laboratory-based. There could be forces that are fundamental and yet almost irrelevant to ordinary chemistry and stars. Fundamental physics would become more layered, less like a single elegant sentence, and more like a larger grammar with several interacting clauses. That would also change the philosophical standing of observation itself. Human beings learned physics through the visible sector because that is the sector that built our bodies, our instruments, and our environment. Light is central to how we measure the world. Our detectors are extensions of senses tuned historically to visible matter. A real dark sector would expose the depth of that observational bias. It would show that the cosmos was never organized around our preferred channels of access. We simply began with the part that talked back most loudly to light and charge. The universe as a whole may be far less centered on that sector than our scientific history made it seem. This is one reason the discovery would feel so humbling, not because scientists would be embarrassed to have missed something difficult, but because the hidden sector would remind us that success in one regime easily tempts the mind into overgeneralization. We mastered the visible particles and began to imagine that we were approaching a final list. The dark sector would say no, you are approaching a final list for the matter you're made from. That is still a tremendous achievement, but it is not the same claim. The correction is subtle in wording and enormous in consequence. Even the relationship between particle physics and gravity would get bigger. At present, dark matter is often the main bridge between particle theory and cosmic gravitation. It is the reason large-scale astronomy keeps telling microscopic physics that something is missing. If the dark sector is real and experimentally established, then that bridge becomes more specific. Gravity would no longer be merely the clue that hidden matter exists. It would be the large-scale consequence of a hidden particle system whose local properties are beginning to be known. This could reshape how people think about unification. The old dream of folding everything into one final elegant structure would not disappear, but it would have to account for the fact that hidden sectors may be common or even natural in the underlying theory. Unification, if it exists, may not look like reducing everything to one visible symmetry pattern. It may look like explaining why multiple sectors emerge, how they couple, and why some remain almost invisible. Then there is the effect on scientific language. Terms like dark matter, hidden sector, portal, mediator, and long-lived particle would stop sounding provisional and start sounding ordinary. Textbooks would change tone. Courses would no longer present the standard model and then append dark matter as an unsolved issue in the final week when everyone is already tired. Instead, the visible sector would be taught from the start as part of a broader cosmic matter problem. Students would learn ordinary particles and hidden possibilities as belonging to one connected research program. The history of physics would be rewritten not because past science was mistaken, but because the next layer of reality would have become unavoidable. This expansion would not remain in theory. It would reshape institutions. New experiments would be proposed with sharper motivation. Funding bodies would suddenly understand why hidden particle detectors, beam dump experiments, precision flavor searches, long-lived particle facilities, and cosmological surveys all belong to one shared frontier. Collaborations across particle physics, astrophysics, and cosmology would intensify because each community would hold different pieces of the same hidden puzzle. Some of the most important data might come not from one giant machine but from the synthesis of many methods. Collider events, halo structure, early universe constraints, underground scattering limits, rare decays, and high-intensity beam experiments would all become parts of one integrated effort to map the hidden sector. There is also a more basic emotional consequence. If the dark sector is real, then every confirmed signal becomes an opening rather than a conclusion. The discovery of the Higgs completed something expected. The discovery of a hidden sector mediator would begin something larger. It would raise immediate questions about population, hierarchy, stability, coupling, cosmological history, and internal structure. Is the first mediator the main one or only one among several? Is dark matter one particle, or many? Are there hidden bound states? Does the dark sector undergo phase transitions of its own? Did those transitions leave any imprint on the universe? Are there relic particles still around that have escaped every current search? Every answer would produce several new lines of inquiry. That is why everything gets bigger rather than simply clearer. Discovery in this case would not narrow the world into a neat corrected version of the old picture. It would enlarge the space of what counts as physically relevant. It would enlarge the timescale we care about, because the earliest universe would become even more important. It would enlarge the set of experiments that matter. It would enlarge the meaning of matter, force, and sector. It would enlarge the gap between local human intuition and cosmic reality. And perhaps most importantly, it would enlarge the frontier in a way physics has not experienced very often since the establishment of the standard model. There is another side to this as well. A real dark sector would not just make the universe conceptually larger, it would make it more ordinary in a strange way. Right now, dark matter is often treated as a single great exception, an awkward, unseen ingredient that gravity insists on, and experiments have not yet explained. But a hidden sector would normalize the idea that unseen matter is not exceptional at all. It would be a proper component of the universe with its own rules. That does not make it less astonishing. It makes it less like a cosmic accounting error, and more like a legitimate part of nature that we were late in recognizing. The universe would not become more mysterious in the sense of less understandable. It would become more populated in the sense of having more to understand, and that may be the most important change of all. The hidden sector, if real, would tell us that the great unanswered questions in physics are not isolated holes in an otherwise finished structure. They're connected signs that the structure itself extends farther than we thought. Dark matter, the incompleteness of the standard model, the search for new forces, the behavior of the early universe, the formation of cosmic structure, the collider hunt for weak portals, all of these would snap together into one broader story. The world would not merely contain one more particle, it would contain another domain of particle physics. That is why the prospect is so unsettling to people who understand the field best. They know that a dark sector discovery would not leave the rest of physics in place with one line added to the chart. It would pull on everything. It would pull on cosmology, on collider strategy, on detector design, on theory, on pedagogy, on the philosophy of what counts as a fundamental inventory. It would make our previous confidence look narrower without making it foolish, and it would leave us with the strange and very serious task of learning how to describe a universe that was never just made of the matter that happened to notice us back. Once that happens, the question is no longer whether the curtain has moved. The question becomes what sort of universe is standing behind it, and how much of what we have called reality was only the bright front portion of a much larger stage. And that is where the story becomes most interesting, because the moment the curtain moves, physics stops asking whether there is something hidden and starts asking what kind of world has been hidden there all along. That is a very different kind of scientific life. Before a discovery, the field lives in a tense condition of possibility. Models compete, searches spread across many channels, every anomaly is handled with suspicion, every null result narrows the map. But once a hidden sector is confirmed in some robust way, the atmosphere changes. The uncertainty does not vanish, not at all, but it changes form. The basic question is no longer whether the dark sector exists. The question becomes how large it is, how it is organized, how it evolved, and how many of our existing ideas have to be revised now that we know visible matter is not alone. That shift would affect almost every level of the subject at once. In the first stage, physicists would move quickly from detection to classification. If the first signal came from a mediator, then the immediate task would be to measure its mass, its lifetime, its coupling to known particles, and the range of decay channels available to it. Does it decay mostly back into ordinary matter? Does it disappear into invisible states? Does it have a narrow width suggesting very weak interaction? Does it appear in more than one production mode? Can it be produced through Higgs-related processes, through rare meson decays, through direct collisions at high energy, through beam experiments? The first confirmed signal would not settle anything. It would create a long list of measurable properties, and those properties would decide whether the hidden sector is sparse and simple, or whether the first discovery is merely the visible edge of something much more involved. This is one of the most important things to understand about the universe after the curtain moves. Discovery would not arrive as a neat final answer. It would arrive as the beginning of a classification problem. Physics would suddenly need a taxonomy for particles and interactions that are not part of the visible standard model. Are there multiple hidden states? Are some stable and others unstable? Is there one dark force or several? Do the hidden particles talk mostly among themselves? Are there hierarchies of mass inside the dark sector? Does the hidden sector have a broken symmetry structure of its own? Is there an analogue of confinement there? Or are the interactions weak and open? Questions that today sound highly theoretical would become practical questions for experiments, because once one piece is real, The rest has to be tested rather than merely imagined. The field would also begin rewriting old data almost immediately. This is not because the old analyses were wrong, but because they were performed under assumptions shaped by a world in which the dark sector was still hypothetical. Once a portal or hidden particle is confirmed, enormous archives of existing collider data would be revisited with sharper and more focused interpretations. Events that once seemed unremarkable might take on new meaning when viewed through the lens of a real mediator. Marginal excesses from previous years would be compared again. Trigger decisions would be reconsidered. Rare decay searches would be reweighted in importance. Precision measurements that once appeared only weakly suggestive might now become crucial consistency checks. In that sense, the universe after the curtain moves would not only generate new experiments, it would retroactively change the scientific value of old ones. That kind of reinterpretation has happened before in physics, but a hidden sector would push it much further, because the new discovery would connect so many different parts of the field. Collider physics would not be the only place under revision. Cosmologists would immediately ask whether the measured properties of the portal are compatible with known relic abundance, structure formation, and early universe constraints. Astrophysicists would revisit halo models and self-interaction limits. Direct detection groups would reframe what scattering signatures are now plausible or suppressed. Beam dump and intensity frontier experiments would suddenly gain a much clearer role in measuring long-lived or feebly coupled states. Instead of a set of related but partly separate efforts, the field would begin to feel like one connected research program centered on a hidden matter sector that has finally become experimentally real. That would have an unusual effect on the intellectual map of physics. For many years, the Standard Model has been the central reference point for particle physics, with dark matter sitting just outside it as a major unsolved problem. After a hidden sector discovery, the Standard Model would still be central for visible matter, but it would no longer be the uncontested center of the whole microscopic story. Teaching, research, and even intuition would start shifting toward a sector-based view of reality. Visible matter would be taught not as the default matter of the universe, but as one set of fields among others. That sounds like a small change in wording, but it would transform the way new students enter the subject. They would no longer think of dark matter as a strange appendix to ordinary physics. They would think of ordinary physics as one region inside a broader matter landscape. That change in perspective would also affect what counts as a successful explanation. Right now, many people still hope for minimal answers. One dark matter particle, one mediator, one tidy extension. But if the first confirmed signal points toward a hidden sector with internal structure, then minimality may stop being the standard by which theories are judged most naturally. Instead, the best theories may be the ones that explain the measured properties of the portal, remain consistent with the Standard Model where required, reproduce cosmology, and predict further hidden sector phenomena in testable ways. The reward would shift from elegance through simplicity to elegance through coherence. A model would not be admired because it adds the fewest ingredients. It would be admired because it organizes a newly larger reality without contradiction. There is something deeply healthy about that. Science is at its best when it lets nature decide what counts as elegant. Human beings like compact stories. We like one cause for one effect and one missing piece for one visible whole. The universe has never promised to satisfy that preference. Sometimes it does, and those are very pleasant years. At other times it turns out that what looked like one missing piece was the edge of a whole, undiscovered structure. If the dark sector is real, then this may be one of those less tidy but more interesting moments. Physics would have to grow up a little further and accept that the underlying world may be layered in ways that are mathematically disciplined, but not especially designed for our convenience. Daily experimental work would change as well. Once a portal is real, detector design would become more strategic. There would be sharper reasons to improve timing systems, long-lived particle sensitivity, low-mass resonance reconstruction, forward acceptance, rare decay triggers, and background rejection for exotic topologies. new dedicated detectors would become easier to justify, not as speculative bets, but as necessary tools for mapping a confirmed hidden sector. Machine upgrades would be discussed in terms of specific hidden signatures rather than broad hope. Collaborations that today feel somewhat niche would become central because they would be measuring parts of the new sector that the largest detectors cannot access well. The field would become more distributed and, in a useful sense, more honest about the fact that one machine rarely tells the full story by itself. Theoretical work would enter a similarly intense period. Once the first measurements are available, the old freedom of theory narrows dramatically. This is often when theory becomes more exciting, not less, because it is forced into contact with reality. Hidden sector models would no longer be judged mainly on broad plausibility. They would be judged on whether they fit concrete data, what coupling strengths are allowed, what relic density mechanisms remain possible, which early universe histories survive, whether the mediator prefers leptons, quarks, or other channels, whether the sector can contain stable dark matter without violating existing cosmological observations, whether there are additional particles that should already have appeared somewhere else. Theory would become more constrained and therefore more powerful. That constraint would likely produce a second wave of surprises. In particle physics, the first discovery often reveals only the simplest accessible part of a deeper structure. Once the W and Z bosons were found, they did not close electroweak theory. They opened further precision tests and deeper questions. The Higgs boson did not end Higgs physics, it began it. The hidden sector mediator would almost certainly work the same way. The first observation would tell us that the sectors communicate. It would not tell us the full inventory on the other side. Physicists would then start looking for companion particles, alternative decay modes, bound state signatures, cosmological consequences, and the possibility that the hidden sector underwent its own phase transitions in the early universe. In other words, the first movement of the curtain would show only that there is something behind it. It would not show the whole room. That room, if it turns out to be rich, would also change our sense of cosmic history in a more personal way. Right now, when people imagine the early universe, they usually picture a hot, dense environment filled with the particles that later gave rise to atoms, stars and galaxies, plus some invisible dark matter component. That mental picture is already challenging enough. A confirmed dark sector would make it more complicated and more concrete. The early universe might have contained visible and hidden plasmas, or at least visible and hidden populations with some degree of interaction. There may have been eras when the dark sector was more active than the visible sector in certain ways. There may have been hidden decays, hidden annihilations, hidden freeze-out or freeze in processes shaping the matter budget that later governed galaxy formation. Cosmic history would stop being merely the prelude to visible structure and become the shared history of multiple sectors. That would change how humans talk about the universe itself. We often describe the cosmos as though the stars and galaxies are the main show and dark matter is an invisible supporting framework. After a real hidden sector discovery, that language would start to look backwards. The luminous structures would still matter enormously to us, because they are where ordinary matter forms complexity, chemistry, planets, and life. But in terms of total matter content, and perhaps in terms of fundamental structure, the visible universe might look more like the exception than the rule. We would still live in the bright part, but we would no longer have much reason to think the bright part is the main part. This would have philosophical consequences, though not mystical ones. It would deepen a lesson science has delivered several times already. We are not at the centre of the cosmos in space. We are not at the centre in time. We are not made of the dominant form of matter, and our senses, even when extended by instruments, were never naturally tuned to the full inventory of reality. Each of those lessons has made science more humbling without making it less powerful. The discovery of a hidden sector would continue that pattern. It would not tell us that the universe is unknowable. It would tell us that knowing it requires overcoming a bias toward the matter that happens, to be convenient for beings like us to detect. there is also a practical human consequence inside the scientific community. A confirmed hidden sector would be one of those rare discoveries that defines careers, departments, and decades of research. Entire groups would pivot, new collaborations would form, old rivalries would become newly productive because different experiments would need to share insights quickly. The boundary between particle physics and cosmology would weaken further, because the most important questions would sit right on that boundary. What is the dark relic? How does the portal behave? What does structure formation now imply? Which experiments can measure the coupling best? Which can measure the lifetime? Which can test self-interactions? The subject would become broader and more integrated at the same time, and yet, for all that expansion, there would also be a strange return to basics. Physics would once again be doing what it has always done in its most important moments. It would be counting what exists and figuring out how it interacts. That sounds simple, but it is the heart of the discipline. The difference is that after the curtain moves, the counting becomes harder and more honest. We would no longer be counting only the particles that shine through electromagnetic interactions. We would be counting sectors. We would be asking which parts of reality couple strongly to us and which do not. We would be forced to distinguish between the local success of a theory and the total inventory of the universe. That distinction would likely become one of the defining themes of the new era. The standard model would remain a masterpiece, but it would be understood more clearly as a local masterpiece. Its extraordinary predictive success would still deserve admiration, perhaps even more admiration, because it would have captured the visible sector so well while leaving room for another sector to exist quietly alongside it. What would disappear is the temptation to treat that success as almost complete in the cosmic sense. The field would become more modest and more ambitious at once, more modest about what it already knows, more ambitious about what reality may contain. Perhaps the most striking part of the universe after the curtain moves is that the discovery would not feel like the end of mystery. It would feel like mystery becoming better organized. Right now, dark matter is a large unresolved fact. A hidden sector signal would convert that fact into a research territory. Unknown does not mean the same thing in those two cases. An unresolved fact is frustrating because it tells you something is missing without telling you how to look. A research territory is exciting because it contains structure, pathways, measurable quantities, and the promise that each answer will unlock several more. The dark sector would stop being a blank region in the map and become a newly opened country, and that in the end may be the most accurate way to picture it. Not as a magical second universe, not as a sudden collapse of everything we know, but as the discovery that the map of matter was always larger than the visible borders suggested. The bright front portion of reality, the one made of atoms and stars and people and machines and all the things that first taught us physics, would still be there. It would still be real, lawful, and beautifully described, but beyond it, or rather beside it, there would be another population, another set of interactions, another domain whose existence had been written indirectly in gravity, long before it was read directly in experiment. Once that happens, physics does not lose its footing. It gains a larger ground to stand on. The universe becomes less finished, more populated, and much harder to summarize in one clean sentence. That is not a failure of understanding. It is what progress looks like when the world turns out to contain more than one kind of silence. And if the hidden sector is real, then the years after the curtain moves will be remembered not as the moment science ran out of answers, but as the moment it realized that one of its best answers had only ever described the bright side of a much larger reality.